even for a king's ransom? Much more down-to-earth mathematics can be found in commerce and industry. A smelting furnace can involve the production of an alloy from an optimum mix of two or more metals, and that process relies on the mathematics of proportion. These metal alloy sheets are being squeezed out into thinner sheets by heavy rolling mills. They require mathematical precision to determine the correct pressures and forces for the job. In fact, the end product of this factory is unusual. It's a successful enterprise in which money is literally being made day and night. This is the Royal Mint in South Wales. In a sense, these presses are part of a process that stamps a mathematical meaning onto metal, enabling the resulting coins to relate directly to the whole world's economy. And in even a superficial look at what goes on here, you can see that the maths of coins goes much further than might be suggested in the money sums written in a school textbook. Of course, spending money involves arithmetic. But have you ever thought about some of the mathematics of actually making coins and then getting them into your pocket?
This is near the end of the whole process, where the newly struck coins are being gathered up and then individually counted. Whatever the coin, and here this machine is counting 20-pence pieces, the whole process of counting is then double-checked by weighing. That check comes about because the weight of each coin is known. This calculation of the value of the consignment is itself a mathematical operation, in which the underlying measure of value is first being represented in another way, that of weight, before being converted back to give a monetary value.
But the mathematics of coinage isn't restricted to financial manipulations alone. By far the most common shape for a coin is the circular disc.
A coin could be said to embody two of the main planks of mathematics. One plank being the arithmetic of value, the other being the geometry of a coin's shape.
The way in which coins are struck can be seen most easily in the proof coin unit of the mint. Here, coins, such as those made of precious metals like gold and sterling silver, are struck individually. But the general principle of making a coin is the same in automated coin presses as well. Both faces of a coin are struck simultaneously using two dies, or molds, positioned above and below each plain blank. Each die bearing the impression of a face of the coin.
Circular coins may be intricate enough to make, but what about this shape? The humble 20-pence piece. It isn't a fashion statement made by some top designer, but is in fact a careful melding of geometry and technology.
This time, there's a seven-sided blank that's squeezed outwards into the exact shape of the coin as the dies strike each blank. Mathematics is needed when calculating the pressure required to get just the right depth of impression on each face. But that's not all. One attribute any modern coin needs is the ability to roll, notably in vending machines.
Although you may not have thought it, this shape rolls too, because a circle isn't the only shape that will roll. And that's where an understanding of geometry has been essential in the construction of the 20-pence shape.
This coin shape has been designed so that if two parallel lines just touch the outside edge of the coin, the distance between the lines remains constant, wherever the lines touch the coin. And strictly speaking, this shape has more than 7 sides. In fact, there are 14 sides around the edge of a 20p coin. Add the original construction lines and take a closer look at the vertex point between 2 sides. Each vertex is seen to have been rounded off as a separate arc of a circle. Look inside a vending machine, and in slow motion you can see how a 20p piece falls and then rolls smoothly inside the mechanism. But are the days of these intricate designs for coins numbered?
Although the mathematics of coinage has provided a means of formatting society, replacing the need for bartering for food, say, with using coins, the mathematics of electronic money may be somewhat different in a future where all money may be invisible. How will society change? Will we be tempted to spend more of something that we don't see at all? Now there's food for thought.
Let's look at some of the maths to be found on the other side of the world. You might say, seeing down under. If you can endure the lengthy flight to New Zealand, you'll find that it's not only the home of adventure. It also possesses many natural attractions, like the hot springs of Rotorua, or the indigenous wildlife. New Zealand boasts the smallest dolphin in the world. And there's the strong, centuries-old culture of the Maori. The Maori culture is famous for its use of patterns which are designed to tell a story. But this is only one aspect of the mathematics that impinges on their lives. On the shores of Lake Rotoiti, you can find several marae, or Maori communities. This is the Rakeio marae. And even though few members of a marae would claim to be mathematicians, you can find them working mathematically, in effect, seeing through mathematics.
Well, I guess Māori people have a very distinctive culture, and we're very proud of that. And I guess that's one of the reasons people come to New Zealand, is to see something of the Māori culture. So that's a venture that my family have got into at the marae here. Tourist people come out and have a concert and look through the meeting house and then share a meal together, and they have a hangi and steamed pudding. For Māori people, we have this notion of manaakitanga, which is hospitality, and that's really important to us. And so, depending on the occasion, makes a difference as to how much food they might prepare. And when the women are working out how much steamed pudding to prepare per person, they'd use a different ratio calculation, because the non-Māori people tend to eat different proportions, particularly of steamed pudding. I think as a people we tend to be very visually orientated, and what I find really intriguing, I said to one of the Māori women one day, how do you know when you're going to run out of flour? How do you know when you have to reorder again? Because Māori people do think a lot in terms of budget in these days when things are really tight. And we were in the storeroom, and there was a sack of flour there that would have come to, say, just above my knee, and there was another half sack of flour leaning next to it. And I said, for instance, do you know how long that flour is going to last? And when do you think you'll have to order some more flour? And she said to me, see my bucket over there? And she pointed to a sort of a plastic bucket about this size. And she said, well, for instance, I know that the flour that fills that would cook 2 steamed puddings and a Māori bread. And so she said, so I know that's how much I need. And then she looked at the sack of flour, and then with her hand she sort of went like this, and then went like that, sort of looking down as she looked at the sack of flour. And she said, well, for instance, I can tell that 3 of my buckets would fit into that half sack, so that's 3 days. And so therefore in the full sack that would be 6 days. So I'd probably have to buy some more flour in 8 or 9 days. And on talking to the women that I interviewed in my study, they don't see what they're doing as maths. What really saddened me, they see maths as something you do inside a classroom, and it's something that has calculations and numbers, and it tends to be more abstract rather than what they do in an everyday context. So they saw themselves as not being successful at mathematics or even users of mathematics.
The Maori have been exposed to what we call mathematics for some time. The earliest Maori book of sums dates back to 1858 and is a translation by Henry Taratoa. He was evidently trying to help his fellow Maori get to grips with the colonizers' arithmetic. Here, for instance, is one of the sums they had to do. 114 iari, that's yards, 2 putu, feet, and 3 inihi, inches, at 4 shillings and 8 pence per yard, comes to what? Answer, £26, 15 and 6. Now, the British weights and measurements may seem odd to us now, not just because they're out of date, but because although the language is Maori, the mathematics is English. Nowadays, there's a Maori mathematics curriculum, and it's no longer a straight translation, but a separate document which draws on traditional Maori knowledge. Often the new syllabus is taught entirely in the Maori language.
The school has a high profile for sport, and that would be the main drive for getting the children into as wide a variety of sport as possible. As a math teacher, I like to bring as much mathematics into it. For instance, with these children, recently we've been doing trigonometry. So a lot of the context of the canoes, and I find that has been really valid. They're much more interested in the problems and starting to think a bit more about it. They can take it from here to the classroom very well, and now I'm going to work on taking it out again from the classroom back to here and see, you know, what interchange there is. When the children are paddling and the steersperson's thinking about how close and what the angle is, they're actually thinking in words just like that. Close, tight angle, wide angle, and things like that. When we take it back into the classroom and talk about it, they do see that the angle might be 45 degrees. You know, when they're looking straight across the 2 kiato, the 2 spars, to line it up with the buoy. Or they might see that it's a bit better if it's 40 degrees or a wider angle. And that's fine in the classroom, talking about those sort of quantities. What I'm hoping is that once working around it in the classroom, they can come back out here and actually start thinking of perhaps 45 degrees or 40 degrees or 50 degrees, thinking that way instead of saying a tight angle, a short angle. I want them to be, hopefully, become more mathematically or give a numerical value to the adjectives that they're using in their activity.
Here's another lake in New Zealand with its own story to tell. Lakes have no tides, but here the surface of the water goes up and down, just as if there were a tide. Lake Wakatipu is the 3rd largest lake in the whole country. This is only the central section of the lake. 2 further sections set at right angles give the whole lake an overall Z shape. It's hard to imagine sitting here on the edge of Lake Wakatipu on the South Island of New Zealand. An ancient Maori legend associated with it would interest today's mathematicians.
The Maoris noticed long ago that the lake actually rises and falls in a very rhythmical way. They believed that the lake was shaped like a letter Z because it was formed from the fetal position adopted by a fallen giant in ancient times, and that the rise and fall is, in fact, produced by the heartbeat of the not quite dead warrior. In fact, the water level can change by several centimeters in just 5 minutes. This phenomenon has interested mathematicians who have endeavored to record the water height data all over the lake in the search for a mathematical model of the cause. Monitoring the water's changing height on the shore is relatively straightforward, but away from the water's edge, that task is much more involved. It's not exactly practical to plant a pole in the lake and stay there to take depth readings. So this is a situation where it's possible for data, such as depth, to be worked out by measuring something else. And the changing depth of water in any part of the lake can be calculated using a device which records how the pressure of water above a certain spot has been changing with time. Analysis of the collected data has led to a mathematical model which accounts for the rise and fall in all parts of the lake. As far as the legend is concerned, you could say that mathematics is revealing some of the secrets to the rhythm of the heartbeat of the Maori giant.
As you can see where more modern names have come about, now known as your frog pool.
From one famous New Zealand liquid to another. This is a mud pool that's been set bubbling by thermal activity. It's perhaps one of the last places you might think of finding mathematics. But let's see. What could you say about the order of bubbling events from the study of these patterns? This is the Whakarewa Reserve in Rotorua, New Zealand. Being a thermally active area, the ground underneath here periodically spews up columns of water. And so a geyser like this at play is very much part of the Maori experience. The air all around the reserve is full of a heavy sulphurous smell. So, is there any maths here? Well, there's a lot of data around. There's the temperature of the water, pressure, the frequency of the eruptions. And you could always apply maths to find out what causes that activity. But there's another perspective. This geyser is crucial to the economy of the area. It's essential that it continues to do its stuff and bring in all the tourists. So when a few years ago it seemed that its powers were failing, there was a big worry about it. And when they looked into it, they found that the locals who live around here had all been tapping into the geyser to provide their own private hot tubs in the back garden. Now, since they banned that, the geyser has stabilized. Things have more or less returned to their regular and dramatic natural cycle.
Everywhere you look in New Zealand, you can see mathematical ideas, which perhaps shows that no matter how far you travel in the world, mathematics is going to be with you, even down under. And that's something you can write home about. On the face of it, maps are just attempts to represent reality using mathematical projections. But take another look at that postcard. The countries might seem to you to have been printed the wrong way up, but to a New Zealander, that view of the world was far more reasonable than this. The standard orientation for a map is just a matter of arbitrary convention, although certainly for safety in the air, pilots, for one, need to refer to just one common map.
The map on that screen is a representation of the plane's route. And like all maps, that map stresses some things and ignores others. So if the plane goes in a straight line, we see a graphic representation of a plane going in a straight line. On the flight deck, though, the pilot will be presented with more than one straight line ahead. I asked Captain Jeff Turner to explain the tracking display.
Well, Carmen, the solid magenta line in the centre of the screen here is showing us the track that we are flying, that the aircraft is flying over the ground. The dotted magenta line to the left represents the aircraft's heading in space.
Why are they different? Are they not the same thing?
Well, they would be if there were no wind. The difference is the effect of the wind on the aircraft. As you can see from here, we have a wind from this direction, represented by the arrow there, at 75 knots. And the effect of that on the aircraft is a headwind component of 57 knots and a crosswind component of 49 knots. So the wind is blowing the aircraft off to the right, and the aircraft, the automatic system of the aircraft, is compensating for that by heading into wind.
Some activities, like flying, can be mathematically reconstructed so precisely that you can experience them without even leaving the ground. But there are some experiences that could never be quite the same if they were simulated. What about our valiant bungee jumper, the mathematician with a vested interest in the workings of his subject? Now, there's only one way to experience a bungee jump.
Down for the water. 5, 4, 3, 2, 1!
You've been introduced to a number of examples of seeing through mathematics. A look ranging from commonplace things like the coins many of us keep in our pockets to unusual daredevil feats like this. What we've failed to do, though, even in a journey to the other end of the world, is to find a situation where no mathematics can be seen. A logical deduction would be that mathematics is everywhere.
Years of mathematical modelling, wood, brass and baboon bones.
The dawn of civilization, humans have used everyday materials to create mathematical models of the world around them. One of the earliest models originated at least 10,000 years ago in a village in Central Africa. It's a baboon bone, just a few centimeters long, etched with a mysterious mathematical pattern. What's the meaning of the lines, and why are they separated into groups? One theory is that the lines model the phases of the moon. The two groups in the middle contain 31 lines, roughly the number of days in a lunar month. Perhaps the first line represents a full moon, with a new notch made each day as the moon wanes, then waxes again towards the next full moon. The lines continue on another side of the bone without showing any regular repeating pattern. The monthly lunar cycle doesn't vary very much, and perhaps a different theory is needed to unravel the bone's mysterious markings. There's absolutely no mystery here. The lines serve a very clear purpose. They're part of a model which records the daily passage of the sun across the sky. As the sun rises, it casts shadows which move as the Earth rotates. On most sundials, the shadow shows only the time of day. The shadow is thrown by the gnomon in the center of the dial. Choose a gnomon with the right height, and the sundial can be used to tell the time of day and the time of year. In midsummer, the sun arcs high across the sky and forms only a short shadow. The tip of the shadow traces an arc across the face of the sundial, a curve called a conic section. In midwinter, the tip of the shadow makes only a small arc across the face of the dial. Other lines show the months in between, so this dial models daily and annual cycles of the Earth around the Sun. An astrolabe is even more complex. It models the movements of the entire heavens. Invented by Greek mathematicians and astronomers over 2,000 years ago, the astrolabe reflects a giant mental leap into space.
The Greeks were concerned with modeling the heavens, with providing a model which would be an overall view, an integrated view of how the heavens worked. So what's remarkable about the phenomenon of Greek astronomy is distancing, that getting outside and representing the whole as an integrated model, and the astrolabe is really just a material version of that conceptual leap.
To start with, the model was all in the mind, an imaginary view from space of the Earth and the stars beyond. In their heads, the Greeks pictured the circles made by the equator and the tropics of Cancer and Capricorn, and imagined how they'd look to an observer suspended below the South Pole. Using the method of stereoscopic projection, they converted their mental model from 3 dimensions to just 2. The technique uses the angles of the lines linking the eye to the edges of each circle. If the angles are kept the same, but the lines are extended or shortened, the result is 3 so-called celestial circles projected on the flat equatorial plane. The Greeks, and later the Arabs, made this mental image real by engraving the celestial circles onto brass. They also marked a grid of the local coordinates, lines converging from the observer's horizon and circles joining equal heights from horizontal to 90 degrees. The grid represents all of the sky that's visible to the observer. The rete is a map of the heavens projected into the equatorial plane. It enables the astrolabe to model the movement of the stars across the night sky, from star rise to star set. Here, the star Aquila appears over the observer's horizon. It moves in an arc up and across the sky until it reaches its maximum altitude, or zenith. As the night wears on, Aquila decreases in altitude until it finally sets below the horizon. Navigators and astronomers soon found uses for these heavenly movements modelled in the brass astrolabe.
This is a calculating device which allows you to produce instrumental results for astronomical calculations which would have been very long and tedious. There's also the conceptual aspect of being able to hold the cosmos in your hands and to be able to see how the various movements are related to each other. 7,000
years earlier, the Babylonians were also modelling movements, But their concerns weren't with stars and planets, but with money and goods.
The earliest examples we have of modelling in Babylonian mathematics are the clay tokens, which date the earliest from the 7th millennium BC, and they were used as concrete representations of particular numbers of commodities.
This token represents exactly 60 sheep.
Normally they've been kept and sparkled for another season, or there's no reason why any of you shouldn't do the same. 41 of them.
A single imprint of the token, with the token itself sealed inside, is a delivery note for these 60 sheep. This simple system lasted for nearly 4,000 years.
In the 3rd millennium BC, the Babylonians moved from a very concrete modelling system where they were using tokens to a much more abstract idea where that they were actually, not only were the tokens representing the goods, but they were using signs to represent the tokens representing those numbers of goods.
As a result, records could be kept on clay tablets. This tablet shows wages paid in units of grain.
Now the round signs on the top here are numbers. The very little ones that look like little fingernail impressions are units, and then the circles are tens, and then these bigger circles within circles are 60s. So they were counting in base 60. And on the back of the tablet we have the total grain paid out to the people. The largest numbers are to the left. We've got 1, 2, 3, 4, 5 lots of 600, so that's 3,000. And the 60s here, 1, 2, 3, so that's 3,180. And 1, 2, 3, 4 tens, so that's 3,220. And 1, 2, 3, so that's 3,223, about litres of grain paid out by this man here whose name is written on the bottom of the tablet. The earliest written signs were in fact numbers, that writing was invented specifically for the purposes of mathematical modelling.
Knots were the basis of the mathematical modelling used by a more recent civilization, the South American Incas. They were great ones for keeping records of what they produced or owned. The number of cows owned by a farmer could be represented by knots on a single cord. Unlike the Babylonians, the Incas used a number system with base 10. 122 cows are represented by the knots down this cord. The knots on the other cords represent cows owned by other farmers. The units, tens and hundreds are lined up across the cords, and zeros are represented by the absence of a knot. Groups of cords were called quipus and were used by the Incas to keep records of almost everything, from the population and belongings of a single village to the output of goods from a complete region. Records of deliveries to this Oxford pub used to be kept on special tallies made from flat pieces of wood. The drayman recorded the number of barrels of each type of beer with sets of notches along the edges of the tally. And like most invoices, this 19th century ale account had copies for both buyer and seller.
$166.
でも指の動きは8を取っちゃう。下から取ります。払います。払います。8を払って10を入れる。 はい、じゃあもう一回自分でやってください。はい、79たす12払って。
This is a soroban, a Japanese heaven and earth abacus. Like the Incas, the Japanese model their numbers in base 10. The number that's modelled depends on the position of the wooden beads. On the Japanese soroban, the beads below the line each represent a single unit, and the beads above represent a unit of 5. So, how do you use the soroban to do a simple sum? What's 362 plus 819? First, set the beads to show 362. Add the 9 units from 819. Then add the 10. Finally, add the 800s to give the answer. 1,181. So, who's got it right? Multiplying is much harder, unless you can do most of it by adding. That's the basis of an ancient Indian method, using pen and paper. It uses a simple grid with one of the numbers along the top and the other down one side. The product of each row and column is entered into the appropriate box, with any tens digits written above the diagonal and any units digits written below. Now add up the units in each diagonal. If it comes to more than 10, carry the tens through to the next diagonal. The result is 42780. Using a calculator or even a soroban gives the same answer. Multiplying by adding seems to work. The method was made even simpler by John Napier, a 16th century Scottish mathematician. He produced solid models which became known as Napier's rods or Napier's bones. In this early set, the diagonals go down instead of up, so the tens come below the units. Each bone is a multiplication table for a single number. This 20th century replica has a multiplier rod fixed permanently in place. For this multiplication, just 3 rods are needed, the 3, the 5, and the 7. Reading the diagonals across the 4 line gives 1428. Add a 0 and you've multiplied by 40. Next, read the diagonals across the 7 line. 2499. It takes just one more addition to get the answer. Napier was also famous for the invention of logarithms. To multiply 2 numbers, say 9 and 10, just add the logs together. The answer is in another bit of the table. The new logarithm corresponds to the number 90. Like the astrolabe 1,000 years before, logarithms were much used on ships at sea.
The reason tables were important at the time is that England was a leading maritime nation, and ships relied on determining their position at sea from astronomical navigation, that is, determining their position from the position of the stars. They had to take readings to do that and had to use tables to perform mathematical calculations to determine their longitude. The problem was that increasingly people found there were errors in tables. A random selection, supposedly, in the 1830s and 40s of 40 volumes of printed tables revealed 3,700 known errors. The problem, of course, was not the known errors, those you could compensate for and get correct values. The problem was the insecurity of the unknown errors.
Correcting these errors became the lifelong task of the 19th century English polymath, Charles Babbage.
The story really starts with John Herschel, Babbage's lifelong friend, the famous astronomer. He and Babbage were sitting at the Astronomical Society in 1821 checking tables. These are tables calculated by hand, and they were quite appalled at the discrepancies between the two sets of tables, the expected value and the calculated value. And Babbage, as it were, clasps his hand to his brow and says, "I wish to God these calculations had been executed by steam."
Of course, steam is just humans modelling by mechanical means, and Babbage knew that humans had calculated tables by the method of differences. X squared plus x plus 41 is a simple polynomial. Logarithms are just polynomials writ large. Successive values of the polynomial differ by 2, 4, 6, and so on, which themselves differ by a constant 2. The pattern of differences can be used to calculate a much longer table of values. These humans are using the method of differences to calculate values of the same polynomial, x squared plus x plus 41. Each person fills in one box before passing the table across for the next person to do a single addition in the next column. This division of labour follows the principles of the Scottish economist Adam Smith and was used in the French Revolution to calculate logarithmic tables. Babbage turned this human computation into a division of labour by cogs. Like Napier and others before him, Babbage had turned hard computation into a series of additions.
One of the very difficult things to do with mechanical devices is to get them to perform direct multiplication and division. The advantage of eliminating multiplication and divisions in the mechanism was something that Babbage perceived, and that is the basic principle of his engines.
When x is 0, the polynomial has a value of 41. As it operates, the engine uses the method of differences to compute successive values. This polynomial needs a greater number of simple additions to give the result for each value of x. Why might Babbage have designed his engine to give values which were much too accurate for everyday use?
And one of the speculations is that he was a mathematician, he was a perfectionist, and this was not only for practical use in terms of measurements he would perform, but in terms of pure science, where the precision, if you like, was limitless.
In the world of mathematics, things sometimes come full circle. In the generation after Babbage, the idea of modelling in metal was pushed forward by Lord Kelvin. His tide predictor is a shining example of the coming together of technology and mathematical modelling. Kelvin analysed the factors affecting the tides into independent variables, and the model predicted the tidal pattern resulting from the interaction of these different parameters. In our own 20th century, computing devices constructed from materials both old and new would reveal the continuing power of mathematical models to help predict and control the world.
If you'd like to know more about it,
You're watching BBC Learning Zone. How many spirals can you think of? From a watch spring to a helter-skelter, the OU takes a look now at how spirals can be modelled mathematically.
The spiral, a common shape in nature, it's fascinated people since time began. Spirals occur more frequently than you might imagine. Some are two-dimensional, and some three. Artists in many cultures have been inspired by the spirals in nature, and they feature in the works of art of most world civilizations. In design and in architecture. Although it was never built, in the 1920s, these designs for a new Russian parliament building were exhibited in Moscow and Leningrad. So what is it that's so special about spirals? Just why do people find them so fascinating? How would you describe a spiral? And would your description fit both the shape of this galaxy and the path that this moth takes when it's attracted to a lamp? Or are there several totally different kinds of spirals with totally different descriptions? In this program, we'll be looking at how spirals can be modelled mathematically. Now, much mathematics is to do with classification, with the identification of fundamental features and patterns. Mathematicians try to identify patterns and to describe those features that are the same, and those that are different. So what are the important features of spirals? One feature that isn't important is size. Any spiral can be enlarged or contracted, as in a photograph, but it's still essentially the same spiral. Before trying to identify those features where the similarities and differences between spirals are important, it's useful to think about what is a spiral and what is not. One dictionary definition describes a spiral as something that is
coiled, winding continually about and constantly receding from a centre, whether remaining in the same plane, like a watch spring, or rising in a cone. Winding continually and advancing as if along a cylinder, like the thread of a screw.
Such a definition allows for both flat, two-dimensional spirals that remain in one plane and three-dimensional ones. In fact, every one of the curves that we've seen so far fits that definition of a spiral. When asked to describe a spiral, this is the one that springs most readily to many people's minds. It's sufficiently important to have its own name. It's called a helix. And maybe the most famous example of a helix is this, the double helix of DNA. Two spirals in one. The helix is probably the simplest example of a three-dimensional spiral. But what are the key features from the mathematician's point of view?
If we look at a projection of this spiral from the top, what shape would we see? Well, of course, we see one of the simplest possible shapes, the circle. So one feature of the helix is that it has this circular projection. But this is only one possible direction for projection, only one viewpoint. If we view it from the side, now from this projection there's a wave pattern. What are the key features of this particular wave pattern? Well, all the waves have a constant height, and the distance between successive peaks is always the same. This particular wave pattern is sinusoidal. It's called a sine wave. And these projections can help in obtaining a mathematical model of the helix. The radius of this circle is always the same. But as well as travelling round the circle, we also travel at right angles to the circle at a constant speed. It's this that gives what engineers call the pitch of the helix.
However, even when we allow for differences in their size, we can see that every helix isn't exactly the same as every other one. The relationship between the radius and pitch isn't the same for every helix. So how can we go from one helix to another different one?
One way is by keeping the same distance between the peaks, the same pitch, but changing the radius. The radius of the circle may be bigger or smaller. But we could also keep the same radius but change the pitch. A combination of these two changes would allow us to make any helix we wish. Any helix can be described by the radius of the circle and by the spacing of the peaks related to its pitch.
So a helix can be described as a continuous coil, circular in one projection, and where the distance between successive parts of the coil is always the same. It's like moving around the surface of a cylinder at a steady rate. And rotating the coil makes the spiral itself appear to move. It's the rotation of the coil of a helix that's utilized by this Archimedean screw to raise water. Another obvious feature of all spirals is what is sometimes called their sense. The sense can be anti-clockwise or clockwise. But often the sense of a spiral is just a matter of deciding where it's viewed from. A clockwise spiral can be turned into an anti-clockwise one by reflecting it and vice versa. To keep things simple, in this program we're looking mostly at anti-clockwise spirals, but all the ideas can easily be extended to include clockwise ones. However, there are three-dimensional spirals that are not helices. Just like the helix, the coils on this helter-skelter are a constant distance apart. But this time, the underlying shape is a cone rather than a cylinder. So what are the mathematical features which can be used to model this spiral?
Like the helix, the side projection is a wave pattern. The distance between each successive wave, what's called the frequency, is still a constant. But this time, the heights of the waves, their amplitudes, increase. So the sine wave pattern we had for the helix has been modified. And from the other, perpendicular projection? Well, this projection is another spiral, a two-dimensional one. So in modelling the three-dimensional helter-skelter, we found a two-dimensional spiral as well. To get the effect of conical spirals like the one round a helter-skelter, we need the path of something which both travels around a two-dimensional spiral and along a perpendicular axis at a constant speed. It's a different kind of spiral from the helix. What are the key features of this new two-dimensional spiral? Well, one obvious one is that the distance between successive coils is always the same. It's a constant. So as the spiral is traced out, the distance from the center, the radius, increases by the same amount on each revolution. And although zooming in changes the gap and gives a different spiral, the distance between successive coils is still a constant. And it's the same when zooming out. Spirals with this property form a family of Archimedean spirals. The path of something that simultaneously travels at a constant speed along a perpendicular axis and round a two-dimensional Archimedean spiral is a good mathematical model of the three-dimensional spiral on the helter-skelter.
But what about the spirals on these shells? Do they share any properties with the helter-skelter spiral? How are they the same? And how are they different?
There's still a spiral winding around a cone. And like the helter-skelter spiral, from this projection there's a wave pattern, with peaks with increasing amplitude. But look at the distance between successive peaks, the frequency of the wave. Unlike the helter-skelter spiral, it's not a constant. It's increasing. So this projection is certainly different. Will the other projection be different as well? It is a two-dimensional spiral. But whereas the most striking characteristic of the Archimedean spiral was that the distance between successive coils was the same, here, the gaps between successive coils get bigger on each revolution. So this is a different type of spiral. For the Archimedean spiral, all that zooming achieves is an enlargement or a contraction. But what's happening this time? This time, the spiral itself appears to be unaffected. But it's possible that you might experience an optical illusion caused by the zoom, that the spiral's rotating, although clearly it isn't. Zooming in or out can't rotate the spiral. What it does do is change the place we are viewing it from. So, mark a point on the spiral, then zoom in. Then rotate the spiral, and we're back where we started, still on exactly the same spiral.
In modelling the spiral on the shell, we found a different two-dimensional one. This new spiral fits many natural spirals. This provides a wonderful example of the latest two-dimensional spiral. How does the nautilus grow its shell?
That's where the animal lives, in the body chamber, as it were. These are gas-filled chambers which it cuts off behind it as it grows. So when it hatched out, it was a little tiny thing. And then as it's grown, it lays down partitions behind it. Initially, the partition is filled with seawater, and then it pumps it out and replaces it with gas out of the blood system. And of course, as it grows, it has to put on more and more buoyancy chambers to balance itself, because it floats just neutrally in the water. It swims along within a foot or two of the bottom. It's living in deepish water, off the edge of reefs, and so far as we know, it's primarily a scavenger. If these chambers are not going to implode, they've got to be beautifully engineered.
The beautifully engineered spiral on the Nautilus shell has this interesting property. It isn't affected by a change of scale. If we take any chamber and enlarge it, then it fits the adjacent chamber. The animal has grown at the same rate in two directions. Even more remarkably, the same thing applies to all the chambers. So if all of these chambers are enlarged by the same amount, they all fit into their adjacent chambers, and so on. This property, known as self-similarity, is of great interest to contemporary mathematicians researching into issues like chaos.
The spiral that models the shell of the Nautilus is also a good mathematical model for the spirals on the sunflower, on this galaxy, and on this fir cone. And here there are both clockwise and anti-clockwise spirals. All are members of the same family of spirals. But are they identical? Well, no, there are differences. We've found that spirals in this family are different from both the helix and the Archimedean spiral. For one thing, it's not possible to get from one spiral to the other simply by changing scale. But before modelling them mathematically, we need to identify some of their essential features. One way is to investigate how the distance from the centre, the radius, changes as we go around the spiral. Once again, nature provides a clue.
Moths appear to keep a course by orientating their body at a constant angle to the moon. This reference angle varies depending on the species and helps the moths disperse efficiently. When there appear to be two moons, the moth selects the brighter. As it tries to maintain an angle to this new reference, the moth spirals towards it.
So moths attracted to lamps follow paths that are equiangular spirals. Let's look more closely at this equal angle property.
As the moth travels along the spiral, the path angle, the angle between the direction of its path and the radius, is always the same. So a key feature of equiangular spirals is that the path angle is a constant for any particular spiral. Change the path angle and we get a different spiral in the same family. This graph shows that for equiangular spirals, the relationship between the path angle and the radius is a straight line one. So what's the relationship between path angle and radius for an Archimedean spiral? Well, this time the path angle isn't a constant. The angle changes as the spiral path is followed. It starts off at 90 degrees, and whatever Archimedean spiral we choose, it will always end up at 0 degrees. And this time, plotting path angle against radius definitely doesn't show a simple linear relationship.
So it would seem that looking at what happens to the path angle is a good way of distinguishing between the Archimedean and the equiangular spiral. But what would really be useful would be mathematical models of the real spirals that would allow us to draw the spirals easily. And using the path angle radius relationship isn't the easiest way to draw both spirals. Which means we could do with another way of modelling these spirals. Is there an alternative way of describing these spirals which is more precise? Let's go back to the Archimedean spiral.
We've seen that for Archimedean spirals, there's a constant distance between successive loops. At the end of each complete revolution, any radius is increased by the same amount. Now, instead of looking at the path angle, let's look at this angle, the angle of rotation swept out by the radius. What's the relationship between the radius and this angle? Here, at the end of one revolution, the radius is 2. Then, after 2 revolutions, it's 4. After 3, it's 6. Then 8, and so on. And if we go out on any radial line, the radius of the spiral will always go up by 2 at the end of each revolution. So here, the radius is 1, then 3, then 5, then 7, and so on. The radius and angle are proportional. The radius is always some constant multiple of the angle of rotation. And so, plotting the radius against the angle of rotation gives a straight line graph through the origin.
But we know that equiangular spirals are different. They don't have this property. So what's the relationship between the radius and the angle of rotation for equiangular spirals?
For simplicity, let's compare both models by looking at the values of the radius at the end of each complete revolution. We've seen that for this Archimedean spiral, the values are 2, 4, 6, 8, and so on, and that they lie on a straight line. A straight line which represents the linear relationship between radius and number of revolutions, even when that number is not a whole number. However, for this spiral, the values of the radius are these. This time, the distance doubles each time round, multiplying by 2. The values for complete revolutions lie on this curve. So how does this tell us how the radius and angle of rotation are connected? Well, all the radius values could be rewritten as powers of 2. 4 is 2 to the power of 2, 8 is 2 to the power of 3, and so on. And each power corresponds to the number of revolutions. So each radius value is 2 raised to a power equal to the number of revolutions. But that's true even when the number of revolutions isn't a whole number. That is, to find the radius of any point on this spiral, just calculate 2 to the power of the number of revolutions traveled. Another word for power is exponent, and this family of spirals is often called exponential for this reason. So this equiangular spiral is one where the radius at any point is 2 raised to an exponent, a constant multiple of the angle of rotation. So, Archimedean spirals are represented by a linear relationship between radius and angle of rotation, and equiangular ones by an exponential one.
We've been able to model some two-dimensional spirals by Archimedean spirals and equiangular ones. By adding movement along a perpendicular axis, the Archimedean spiral models the helter-skelter spiral, and the equiangular spiral models the ridge around this shell. Yet more three-dimensional spirals can be modeled by the helix. So have we found every possible family of mathematical spirals, or are there other families? Well, yes. Both the sunflower and the pinecone can also be modelled by yet another spiral, the Fermat spiral. This spiral is also a good model for the path that satellites take in reaching their orbits around the Earth. But there are millions of different spirals.
Why was it that she really never became a nurse? Yes.
And why couldn't she find fulfillment in the jobs that she did and so on? And that question was running through my mind all the time I met her. And sometimes I thought, well, it's because of her class background. Other times I thought it's because she's black. She's come at a time when black people are seen in a certain kind of way and she's forced into these kinds of jobs. And then other times it was because she was a woman. Mm. And then I just had to give up and recognise it was because she was black and of a certain class and a woman, and all of those three wove together in her whole life experience.
And that is generally true for all the cases that we looked at.
I think so.
There's
yes.
class and race and
Right.
ethnicity and the difference between men and women, all playing on each other to define the sort of position and experiences of men and women.
Yes, very much so, in all of the cases that we looked at.
Elaine Stokey, thank you very much for talking to me.
Thank you.
Well, next week we're going to see a program which continues the theme of continuity and change. Now we're going to look at the changing definitions of work and changing patterns of employment, especially as they relate to the work of women, both in and outside the home.
In fact, you can see the programme Stuart was talking about at the same time tomorrow here on BBC Learning Zone. Now on BBC Learning Zone, the story of Florence Nightingale and statistics.
Consumption is caused by a shortage of good air as a result of overcrowding. Infection, indeed.
But according to Professor Galton, you have never directly attempted to refute the statistics supporting germ theory.
Because there is no need.
Yet he states...
It is plainly obvious that the habitual admission of vitiated air will injure the lungs and cause pulmonary disease, just as the admission to the stomach of poisoned food will destroy that organ. Or is that also to be denied? Facts are everything, doctrines are nothing.
Precisely so. And as there is firm statistical evidence to support the contagion theory, if one of your objections to the first chair of statistics going to Professor Galton is that
Does it never occur to the advocates of contagions that there must have been a first case in the world, which could not have received its infection or contagion from any other case, and hence, according to their doctrine, the Supreme Being must have infected it? And is that a notion they're content to believe?
Miss Nightingale, perhaps it is not the time for us to enter into a theological debate.
But you are ordained, Dr. Jowett. You must have views upon the subject.
I do believe the Professor is a man to be trusted. Further, he has both the vision to appreciate the vital necessity of this chair of statistics and, moreover, the influence to bring it about.
But what of his judgment? What is this contagion in which he places so much faith? It implies the communication of disease from person to person by contact, yes?
It does, yes.
It presupposes the existence of certain germs which can be bottled up and conveyed any distance attached to clothing, to merchandise, and especially to woolen stuffs, for which it is supposed to have a particular affection, and to feathers, which of all articles it especially loves. There is no end to the absurdity connected to this doctrine. Yet it is to Galton, the supporter of these theories, that we are to entrust the progress of our chair of statistics.
Miss Nightingale, I fear you underestimate the gentleman.
And my fear is that I do not. His research will only end in endowing some bacillus or microbe, and I do not wish that.
Well then, as you say, Miss Nightingale. Good day to you.
Good day to you, Dr. Jowett.
It had been many years earlier, when Florence Nightingale had first returned from the horrors of nursing in the Crimea, that she begun to see the need to keep accurate statistics, and for them to be put to use. Not that she was alone in the 19th century in recognizing the enormous importance of statistics. The work of the great Belgian statistician Adolphe Quetelet was to have a tremendous influence upon Florence Nightingale. In Britain, the philosopher John Stuart Mill saw the increasing use of statistics as a vital tool in assessing the advances made in society. But other writers, particularly Charles Dickens, were appalled by its growing influence, seeing it in conflict with the intuitive, the human. Florence Nightingale had no such reservations. She'd always loved mathematics, but her special interest in statistics arose out of a practical need in the aftermath of her experience in the Crimea.
I've seen hell. I shall never forget it. Nothing, not the Dales, not the tedious congratulations of a job at which I failed.
You did not fail.
Oh, they died, Parthy. Hundred upon hundreds of young men there before me. Eaten away by disease, they died. There in front of me, in the hospital at Scutari.
You were not responsible for the whole conduct of the war.
But the war was not responsible for their deaths. The military hospitals were. The sufferings of those men, their sufferings and their deaths, they live with me every second. And nothing, oh, not even family, dear Parthy, nothing can take that from my mind. And I do not wish it to be taken from my mind.
You torture yourself.
No, but I am tortured.
You were not responsible for all that happened in the Crimea.
Do you know how one major described the men under him? As animals, and deserving of no more attention than animals. He said I would spoil them by helping to keep them alive, I suppose.
You have changed all that.
Well, I hope they're now seen as decent, brave young men. But that's not enough. What is the use in our recognizing their decency and their bravery if they're still to die like cattle? There must be complete reforms. But how am I to carry them out? A mere woman, marriage fodder, so well past her proper marriageable age. The only marriage I would wish for is this. The union of all the compassion in my heart with the clearest, sharpest, most scientific sense of purpose I can muster. What use else is compassion to anyone?
You should rest, Flo.
Perhaps. But I cannot. God called me out to the Crimea, and he hasn't finished with me yet.
She might have been a mere woman, but she was unlike virtually any other woman of her day. She'd always refused to live out the role of society lady, which she saw as an endless stream of meaningless social engagements. But while the prejudice against her gender was a huge obstacle, her class background was a tremendous asset. Indeed, had she not been so very well connected, it's unlikely the authorities in the Crimea would have tolerated her at all. Men injured or taken sick in action in the Crimea had to endure a sea crossing of hundreds of miles before even reaching the hospital at Scutari. There, Florence Nightingale did all she could to reform on the spot the practices of the army hospital. But she became convinced that most of the deaths were a product of the hospitalization itself. As far as she was able, she systematized the utterly chaotic record-keeping at Scutari, and the figures she was able to produce supported her argument. In Dr. William Farr, a doctor turned statistician, she found an ally.
So, these are the figures, Dr. Farr. Now, what to do with them?
We must present them as cogently as possible.
Indeed. But first, if you could just help me to clarify, according to Quetelet,
Human behaviour need not be considered indeterminate and unpredictable, a matter of each individual shooting off in his own direction with no rhyme or reason whatsoever, yes?
That's right. He believes that human beings are in some ways akin to natural phenomena, with behaviour that can be measured under a variety of different circumstances.
And these measures can then be used to predict behaviour in the future.
But not the behaviour of any one individual, of course, Miss Nightingale. Rather, any group will be subject to certain laws of probability.
Laws of probability, yes. So, statistics may become a revelation of God's laws, for he has laws applying to all phenomena, not merely the physical sciences, and we must act within those laws. Yes, that is the real meaning of statistics. They lead us to appreciate the laws of God so that we may act effectively within those laws.
That is an inspiring interpretation.
Well, it is my belief that God wills only good. He places evil in the world solely to stimulate our human faculties in an unremitting struggle against every form of it, and struggle we shall. I have the whole world of military and medical men, almost the whole world, predisposed to dismiss the theories of this meddlesome woman. So, how should we proceed?
First, let us look closely at the analysis by geography. So clearly, mortality reached its highest point within the British hospitals themselves.
Yes.
We must choose our targets, Miss Nightingale. We know we are dealing with the truth, but there are many truths. We must decide which to present. And the first and clearest, to my way of understanding, is that this enormous number of deaths happened in those hospitals, and that number decreased dramatically as a result of the measures taken affecting the hygiene in those hospitals.
Yes.
So, the peak was reached in January 1855.
83 died of wounds, 324 from various other causes, and 2,761 from avoidable diseases. Now, had the deaths continued at that rate, the entire army would have been annihilated in under a year without a shot being fired.
Indeed. Now, you need to show diagrammatically the fall from that peak related to the measures which you took.
A circle then, with the full circle representing the 12 months of the year.
And the proportion of the circumference given to each month to correspond to the number of deaths in that month.
Yes. We could take it further. If we use the area, it makes it clearer. If we divide the circle into the 12 parts, then we shade in the area of each. And that gives a clearer impression of magnitude.
That is much clearer.
Perhaps my sister could draw them better for me. Or my friend Hilary, she's an artist, she may be able to.
For Florence Nightingale, statistics were a tool, the most important tool available, which she learned to use with considerable skill in order to further the cause she believed in so passionately. Yet it was not in her comprehension of statistical concepts that she broke any new ground, but rather their visual presentation. It was not enough to leave them as cold figures. They had to be presented in a way which would bring them boldly to life through use of line, of shape, of colour, and in a way that would change public opinion. For it was opinion, both public opinion and the entrenched opinion of those in power, which she intended to change.
The visual presentation is quite startling, quite startling.
I want everyone to understand. No hiding behind the supposed incomprehensibility of statistics. These figures must be as clear as a picture. They must tell a story as clearly as does
a picture of the crucifixion.
Quite so.
Here we have the death rate at Scutari from October 1854 to June 1855, calculated on an annual basis as a fraction of patient population. Now, it reached 415% in February. The sanitary reforms began in March, and well, you can see the results.
Indeed. And this one?
A comparison between mortality of English males in the general population and those in the army, categorized by disease. Well, as you can see, joining the army is not to be recommended.
Indeed. But isn't that to be expected to some extent, given their occupation?
But these are not the soldiers in the Crimea, Dr. Farr. No, these are ordinary soldiers, mostly in barracks. Yet they die at almost double the rate of the rest of the population.
Shocking.
Now, as you can see, it applies to all age ranges. Ages 25 to 30, percentage of deaths of English males, 9.2. Percentage of deaths in English army at home, 18.3.
Astounding.
Well, it ought to be. But when you see how the army are made to live, it is only astounding that there is not more disease. And the army are picked men. The young, strong, physically fit, not the old, the infants, the infirm, yet they die at twice the rate of the rest of the population. Now, these statistics show that 1,500 soldiers a year are as certainly killed by this neglect of their living conditions as if they were drawn up on Salisbury Plain and shot.
So when our young men enlist into the army, they are enlisting into an almost certain death in the barracks.
Now here, look. It is vital to make clear the loss of manpower to the army as a whole. If the military amongst the readers of our report are not moved by normal human decency, and I have no reason to suppose they would be, they may yet be moved by self-interest.
Perhaps.
Let us suppose that 10,000 healthy, new, young 20-year-olds are recruited into the army every year. By the end of 20 years, that number will have been reduced to about 7,000. Now, leaving aside the human tragedy, that represents a loss of 29% of manpower. I've made a positive projection showing what the strength of the army would be if the conditions under which they lived were up to the standard of the rest of the population. I've assumed the civilian rate of mortality and that the relationship between mortality and invalidity remain the same. Result?
An increase in the strength of the army of about 1,000.
Correct.
And what are these?
I call those my coxcombs. They are rather vulgar, aren't they?
They're certainly very arresting.
Scutari. The pink wedges for deaths from wounds, the blue wedges, deaths from avoidable diseases, and the grey wedges for deaths from various other causes. How far each wedge projects from the centre visually emphasizes the variation in the number of deaths.
Quite brilliant.
These representations must make clear to even the most dim-witted parliamentarian the irrefutable strength of our case.
Her arguments were pressed through a royal commission and the publication of her notes. And her views, so strongly supported statistically, were indeed accepted, leading to a series of fundamental reforms of army hospitals and living conditions, both in Britain and in many other parts of the world. Yet however well the information is presented, it must first be collected, and collected accurately. This was another area of concern to which Florence Nightingale turned. Despite continual poor health, she often visited Claydon House in Buckinghamshire, the home of her sister Parthenope, Lady Burney.
Tell me, Parthenope, in all the work I did in preparation for the report to the Royal Commission, or for my notes, what do you think hampered me more than anything? The War Office?
No, though a fair guess.
Oh, then, the medical men, or the government itself. Let me tell you about record-keeping at Scutari. There,
deaths were noted down on 3 separate registers. First, the adjutant's daily headroll of soldiers' burials, on which one would presume that no one was entered who wasn't buried, though...
There may have been some buried who were not entered.
Perfectly possible. Second, the medical officer's return, in regard to which it is quite certain that hundreds of men were buried who never appeared on it. And third, the return made in the orderly room, which is only remarkable in that it gives a totally different account of the deaths from either of the others. Now, admittedly, these returns are an extreme case.
But are you saying that in compiling the notes, your greatest problem was in finding accurate figures?
Accurate and standardized.
Surely some hospitals keep adequate records.
Yes, but there can be no possibility of comparing the data from one institution with that from another, as each has its own classification, even its own set of definitions. In their present state, these records bear as much relation to each other as an indefinite number of unrelated astronomical observations would bear to the progress of astronomy.
Yes, of course.
Ah, Harry.
Together, Florence Nightingale and William Farr produced model forms to standardize the collection of data. But despite being presented at the International Statistical Congress in London in 1860, these forms were never adopted within the hospitals themselves. While they were generally welcomed in principle, they were definitely not, to use the modern term, user-friendly, being tremendously complicated and time-consuming to complete. There was also much debate over the categories of illness she adopted, debate connected to the theory of contagion, a theory to which Florence Nightingale refused to subscribe, despite the overwhelming evidence in its favour. So, while many of her other projects, dealing with matters as diverse as domestic hygiene and sanitation in India, were to bear fruit, this attempt to standardise the collection of hospital statistics failed. Her obstinacy in the controversy about germ theory dogged her all her life. But perhaps even more important was her implacable opposition to the study of theoretical statistics.
You have not reconsidered?
I have not reconsidered. You see, for me, statistics is the most important science in the world.
I know that, Miss Nightingale, and Professor Galton.
For upon it depends the practical application of every other science and of every other art. It is the one science essential to all social and political administration, all education and organization based on experience, for only it gives exact results of our experience.
I do believe the Professor understands this, Miss Nightingale, and in his view, such a science must have a secure theoretical base, which is why he believes the chair must concern itself with research into statistics itself.
No. No. Have we not already an absolute plethora of figures and literary figuraticians creating a veritable waltz of numbers? What have I ever achieved? Has it not all been precisely from the application of statistics? It is its uses which must be disseminated, not its capacity for endless theorizing.
Miss Nightingale, by this attitude you jeopardize the entire undertaking.
Then let it be jeopardized. Let it be abandoned. We have great work to do, nothing less than countering the grotesque products of the sheer stupidity of our entire political system. Is that to be achieved by theories of statistics? Applied statistics. That must be the name of the chair, and that must be its function.
I do not believe Professor Galton will accept such a limitation, Miss Nightingale, and I call upon you...
Then let him not accept it. And I, in turn, will revoke the donation I had intended. If Professor Galton and his theoretical statistics are the price to pay for a chair in the discipline, then that price is too high. Statistics exists to serve a purpose, to support us in our fight for the alleviation of suffering. It is not there to serve as anyone's intellectual plaything. I shall not reconsider.
In 1911, 1 year after the death of Florence Nightingale, the first Department of Applied Statistics was established at University College London. The study of statistical theory had to wait a little longer. For her, statistics were not a matter of dry and dusty figures. She cared passionately about the plight of others and believed that statistics were the means by which vitally needed social changes might be implemented.
That's all for now on BBC Learning Zone, but do join us again at midnight here on BBC Two.
But what was causing the problem? The finger of suspicion pointed to a linseed oil mill. Certainly all the asthma sufferers had commented on the smell of linseed oil. But detailed investigations showed that the flaxseed particles involved in linseed oil production were too heavy to be windborne. Linseed could not have caused the asthma. But the same factory also produced an oil with no smell, castor oil. And castor bean dust was light enough to be windborne.
Some years ago, I reported quite a large number of cases of asthma which were occasioned by the grinding of castor bean dust in a castor bean mill in Toledo. There were some 200 of these patients living within a radius of a mile or so of this plant. The matter got into the courts, and this factory was prohibited from having anything to do with the handling of castor beans. They were not even allowed to import a single castor bean, much less grind any.
You awake again? You feeling a bit better? Where are you? You're in hospital.
Asthma is a condition in which the bronchial tubes are unduly irritable, what I call twitchy tubes, so that if a patient who's got these twitchy tubes inhales something to which they're likely to be irritable, namely an allergen, such as grass pollen or something like that, or maybe fumes or something like that, then in that situation the airways will respond and narrow down. Once you've got narrowed tubes, it's more difficult to get air in and out, and the patient will complain of breathlessness, wheeziness, and sometimes cough or tightness in the chest.
I'm just going to pass this over the back of the tongue.
It's quite red, isn't it?
Yes, it's quite inflamed, isn't it, there? Yes.
Many people regard certain things as causing asthma, when really what they mean is causing the acute attack in somebody who has already got asthma, and there is quite a difference. It is, of course, very common. It occurs in about 15% of primary school children and is twice as common in boys as in girls. In adulthood, it occurs in about 6% of the UK population and tends to be more common in women than men. The reasons for this are not clear. Nevertheless, of course, it does represent a very significant workload on the NHS. The curious thing about asthma is that it is very variable. Sometimes you'll be fine, sometimes you'll be bad, and occasionally it's very obvious what has set you off. You've maybe been in contact with a cat and you get wheezy. But you do sometimes find times when all of a sudden quite a lot of people have asthma, a sort of epidemic if you like. Some of these causes are identifiable and obvious, others are a complete mystery.
And it was just this type of occasional serious outbreak of severe asthma symptoms, each lasting only about 4 hours, that was seen at casualty units in Barcelona hospitals in the 1980s. The very first attack was on August the 5th, 1981.
Our residents noticed that in the emergency room came at that time much more asthmatic people than usual. You know? We used to have about 1 or 2 asthmatics per day, and at these days, some of these days, we notice perhaps 15, 20 patients. If they arrive at any hospital in Barcelona, normally they respond very well to the bronchodilators, but they were really very severe asthmatics. And We have to say that normally the crisis began during walking in the street, and it was a very, very sudden attack of asthma.
In the autumn of 1984, after 7 of these serious but short-lived asthma outbreaks, the Barcelona Asthma Collaborative Group was formed. A leading member of this group was Dr. Josep Anto.
The group was made up of about 20 different people coming from very different specialities. We had physicians, epidemiologists, but also chemists, biologists, meteorologists, and it was very exciting to be involved in such kind of multidisciplinary group. The first task that the group took at that time was to review the available data and to select the best investigation design for the future. And it was not easy, especially because different points of view arise from the different specialities. And we finally decided to establish a very large register of emergency room admissions, including all the hospitals in the city, providing populational-based data, not only data for one hospital, but also data for all the residents in the city, and to provide a very good definition of asthma.
The information that was collected for the register was the name, age, and date and time of arrival for every patient admitted to casualty suffering from either chronic bronchitis or asthma. On the 26th of November 1984, shortly after the formation of the group, there was yet another severe asthma outbreak in Barcelona. We can see the evidence for the outbreak in this time series plot. Time runs along the horizontal axis from the 18th of November to the 18th of December. The vertical axis represents the number of asthma admissions per day. And because the points are ordered over time, it makes sense to join them up with lines. There does indeed appear to have been a big increase in the number of asthma cases on the 26th of November. But does this tell us anything?
You've got to remember that when you've got any collection of numbers, one of them, maybe more if they're equal, but one of them is going to be the biggest. Whether there's anything sort of significant about this biggest number is a tricky question. Maybe it's the biggest number because there's something special causing it, but maybe it's just an outcome of a normal level of random variation. You have to be more sophisticated to check this kind of thing out, and we have to use statistical models. The Barcelona group did this, and they found that such a peak as this was very unlikely to have occurred just by chance, and is more likely to have some other kind of cause.
So there's clearly a bunching, what statisticians would call a cluster of asthma outbreaks in time. But there was also strong evidence of a different type of clustering, a geographical one. This map of Barcelona shows its administrative districts. And here are the locations of the asthma attacks of November the 26th, 1984. Many happened in or close to District 5. But the attacks occurred during the day, and as this region is the administrative and historical centre of the city, the daytime population is going to be greater than the resident population. So is there only a clustering in the centre of Barcelona because there are more people there, rather than because they are more likely to have asthma attacks? To eliminate this effect, the group took the numbers and adjusted them. They calculated the number of attacks per 100,000 people, a rate of attack, and plotted those instead across each region. The higher the rate, the more intense the colour. And the group found that the apparent cluster around the city centre still showed up. But there may be other reasons why this apparent clustering is misleading.
Well, these rates have also actually been age standardized. Suppose the condition of interest is particularly prevalent in say, old people. Then, if you observe a geographical cluster of cases, maybe that's just because there are a lot of old people thereabouts. And sure enough, Barcelona's District 5 does have rather a lot of elderly folk. Now, the way the age standardization is done is to look at numbers of sufferers in each age group. And what you do is adjust the total number of people in each age group to better match the age profile of the entire city. And then you adjust the numbers of sufferers in each age group by exactly the same factor. And then you calculate the rate from these adjusted figures, and you've got rid of the effect of different age distributions.
The Barcelona investigators checked out the geographical distribution of age standardized rates for each of the first 12 asthma outbreaks.
The data that we got from the register was enough not only to demonstrate the occurrence of different asthma outbreaks, but also to provide good descriptions of the geographical and time patterns of such outbreaks. And in both cases we observed a very striking clustering. Most of the cases were clustered around noon, some days earlier in the morning, some days perhaps a bit later in the afternoon, but always with a very striking time cluster. And there was not only a time cluster, but also a geographical cluster, so people experienced the asthma attacks at the same time and in the same place. The geographical cluster was mostly around the districts near to the harbor of the city, and the overall picture was one that can be easily labeled as a point source outbreak.
But if there was a point source, where exactly was it? They asked local agencies like the police, the harbour administration, the fire brigade and the local council to identify any unusual environmental agent which was produced on asthma outbreak days and so might be related to the attacks. No evidence was forthcoming until in early 1987, nearly 6 years after the first epidemic, harbour authorities reported that outbreaks had twice occurred on the same days as soybean unloading. But surely soybeans couldn't be to blame.
When we were aware about the ship unloading soybeans coming from Toledo, Ohio, we didn't expect soybeans be associated with asthma outbreaks. And this was mainly because there were no reports in the scientific literature linking soybeans with asthma. And on the other hand, soybeans is a worldwide used product, and no evidence is that can produce asthma outbreaks. It was strange, but we were aware about reports showing that coffee workers are sensitized to castor bean. And this is due to the fact that the bags used for coffee have been used before to transport castor beans. And castor bean is a very allergenic product indeed. So we thought that perhaps the ship had unloaded or transported castor beans before, or that soybeans could have been contaminated with castor bean dust. And our preliminary expectations were more related to castor beans rather than to soybeans. But the results were striking for us, so we were really surprised to see that patients were mostly negative to the allergens that had been included in the test, but specifically positive to soybean.
Later that same year, on September the 4th, there was another very nasty outbreak. Indeed, this time there were 2 deaths. So although the evidence for soybeans as the direct cause of the outbreaks was far from overwhelming, the Barcelona authorities decided to stop soybean unloading while its guilt or innocence was investigated. After all, they had no alternative theory, and the problem was now of great public concern. Soybean unloading in the harbour was stopped for 3 months while the theory was investigated. This investigation had 3 main parts, each involving yet more statistical analysis. First, the team looked back at the records for 1985 to 86. They looked at the number of asthma admissions to hospital on each day. And although it's hard to make out the fine detail in this picture, the asthma epidemic days do stand out. The investigators then looked at how the unloading of various products in the harbour, including soybeans, matched up with the asthma outbreak days. This table shows that during the 468 days on which there were no soybean unloadings, there was never an asthma outbreak. All 13 outbreak days happened during the 262 days on which soybean unloading took place. But why weren't there 262 asthma epidemics? Well, the weather conditions also played their part. The winds had to blow from the southwest, and they had to be strong enough to carry the dust over the city, but not so strong that the dust wouldn't settle. Only soybean unloadings matched up so strikingly with the epidemic days. It's true that 7 outbreak days did coincide with the 406 cotton unloading days. But 6 more outbreaks occurred on days when there was no cotton unloading. A second check on the soybean hypothesis involved laboratory work. Blood samples were taken from some 86 of the victims of the asthma outbreaks in September 1987, and they were tested to see if they reacted to soybean extracts. 64 of the 86 samples, about 3/4, did react, a high proportion. But how can we be sure that it was breathing in soybean dust that really caused these people to have asthma attacks? How do we know that 3/4 of the unaffected population's blood would not react in the same way? To examine this, the investigators did a case control study. But what exactly is a case control study?
In a case control study, the people who are of interest, the cases, the ones that suffered from asthma in this case, they're compared with another load of people, the controls, who don't suffer from the asthma. And what's more, the cases are carefully matched with the controls in terms of sort of everything else, except for the fact that one lot gets asthma and the other doesn't. The idea then is that if we measure something like the serum reactivity to soybean in this case, any difference between the case and control groups can be linked with the only other difference there is between them, which is that one lot suffers from asthma and the other lot didn't. In the Barcelona study, the 86 cases were each matched with an individual control in terms of sex, age, and place of residence.
The results showed that of the 64 reacting cases, 61 were paired with controls who did not react. Again, strong evidence implicating soybean dust in the asthma epidemics. Another way the team checked their theory was by comparing the amount of soybean dust in the air on epidemic days with the amount on non-epidemic days. They did this by sampling the air. Air samplers were placed in a variety of locations throughout the city.
We were expecting to find different spores of fungus from the usual ones, so what we found was really surprising. We found vegetable cells, and in the beginning we were totally unable to identify what they were. Later on, when it was suspected that the asthma outbreaks were related to the emissions of soybean dust, from the points of view of the people having asthma attacks on the key days, we were able to identify a large amount of particles of between 8 and 10 microns in size that we had never seen before. Now this is an interdisciplinary study, and so other members of the group were able to supply me with samples of soybean dust from the ships unloading in the port. This is an air sample that was gathered in the city on one of the outbreak days. And this trumpet cell matches exactly ones found in the walls of soybeans.
It was found that the average soybean level in the air was over 7,000 units per cubic meter on epidemic days, as opposed to little more than 400 on non-epidemic days. Further statistical investigations confirmed that these differences are probably not just a consequence of random variation. So all in all, the accumulated evidence makes the link between soybean dust and asthma epidemic outbreaks pretty clear. But the collaborative group's detective work was even more specific. When investigating the connection between the asthma days and the unloading of soybeans, the group had been able to look at results for each of 2 separate silos in entirely different parts of the port. This one, which they called Silo A, and this one, Silo B. The group found that of the 13 epidemic days in 1986 to 87, 9 were associated with unloading at silo A only, and a further 3 when unloading took place at both silos. The evidence pointed clearly to silo A as the source of the problem. But why? Was it because silo A is much nearer to the city than silo B?
Well, the problem was that silo A did not have appropriate back filters at the top of the silo. And due to the absence of filters, we estimated that during an unloading day, probably more than 1 ton of dust could have been spread through the air. So the important consequence of this observation was that we expected that after installing filters at the top of the silo, the asthma outbreaks should have been eliminated. And indeed, this was the case. We were able to stop unloadings in silo A for 3 months, and during this period, they installed appropriate filters. And at the end of this period, unloading of soybeans were taking place again at their normal pace. And during the following years, we have been able to keep the register of asthma admissions active, showing that no other outbreaks have occurred.
The several years it took to solve the mystery of the Barcelona asthma epidemics demonstrates that the problem was not a trivial one. But need the investigation have taken so long?
Well, this study wasn't just a one-off, where you asked a question, got some data, got the answer. Instead, just like, I guess, virtually any other real-world major statistical investigation, indeed like any other real-world scientific investigation, it proceeded piecemeal. It had some initial ideas and questions, collected some data, got some answers, but some of these perhaps rather equivocal, some new ideas as well. You'd like to test out both further the old questions and some of the new ones, so you get some more data, get some more answers, some useful, some not so, some new ideas, some more aspects to look into, get some more data again, and so on, and so on, and so on.
In recent years, soybeans have been regarded as hypoallergenic, that is, harmless in connection with health problems like asthma. So soybeans were not immediately suspected as a cause of the outbreaks. But their effect on asthma had been predicted much earlier. Back in the 1930s, at the time of the investigation of the Toledo castor oil mill.
Since that time, this castor bean division of the plant has been engaged in grinding soybeans and extracting the oil. So far, I have failed to see a single case of soybean sensitivity in this vicinity in a matter of 2 years. I feel certain I will, sooner or later. But I think it may be rather an interesting observation as to the necessity of time for many of these asthmatic individuals previously sensitized to castor bean dust to develop sensitivity to this other substance.
So what is the future of investigations into the causes of asthma?
Since the Barcelona outbreak, further episodes have been seen at other Spanish ports where soya has been unloaded. But even more interestingly is that in retrospect, outbreaks of asthma occurring in New Orleans in the 1960s have in all probability now been attributed to soybean exposure, which was totally unsuspected at the time. So I think we can go on from here and perhaps even backwards and identify the causes of some of these epidemics of asthma.
I tended to think before we made the programme that the cleaning would be a local company just from round the corner. In fact, the company that did the cleaning in Bradford were an Australian multinational. Whilst they still employed the same people to do it, it was actually organised and there were big economies of scale from doing it multinationally. And of course NFC one of the things that it was enabled to do as a result of the shift was that it could actually behave internationally. In fact, as we know, it overstretched itself, and that was one of its problems. But the international, the local, global distinctions were important in that case too.
Neil, thank you very much indeed. Next time we'll be taking a look at Britain in Europe, at Europe in Britain, and at the thorny question of national sovereignty.
This is BBC Learning Zone. On BBC Learning Zone now, juggling and its mathematical applications. Caught in time.
Juggling is becoming very popular, and not just as a spectator activity. It's now a very common amateur pastime with children and adults alike.
Okay, watch the ball leaving one of my hands.
It's even used in the classroom.
I want you to describe what that path is and also why it follows that path. Everyone got it? Question number 1, path followed by a juggling ball. Who can help us? Emma?
It follows the shape of a parabola.
Yeah, and why does it do that?
Because the acceleration is in a vertical movement, with no horizontal forces acting upon it.
Great, yep. Okay, question number 2. Why is juggling with 3 objects of different mass no problem?
But why is juggling so popular? What exactly is juggling?
If you look it up in a dictionary, it says to deceive by manipulation. But these days, juggling is generally regarded as a hobby or an entertainment and not usually to deceive. But it's always the manipulation of objects, usually keeping objects in motion. And this single definition seems to cover all the forms that people use with juggling, from 1 ball while doing gymnastics through to 9 balls while going for world record attempts.
1, 2, 3, 4, 5, 6, 7, and he's done it. No, yes, he did it.
Congratulations, Mario. Yeah, great stuff, right here.
That was very close.
I know.
Thinking, Carter.
Excellent. Congratulations on your world record.
Thank you.
There are many different types of juggling. There's the classical juggling, which everybody thinks of as being what the clown does with a set of balls or juggling clubs. Other objects are juggled as well. Rings, which are sort of like plates with holes punched in them. And as well as those, people juggle bowling balls and chainsaws, which everybody asks you about. But there are other types of juggling as well. There's a thing called the devil stick, which is a long rod, and then you've got 2 sticks like chopsticks, only a bit bigger, that you hold in your hand, and you bat this long rod back and forth between them. There's a thing called a diablo, which is like a double-ended spinning top, which you have, again, 2 poles, and this time with a string between them, and you keep the diablo going on the string. There are things called shaker cups, and there's all sorts of different objects you can juggle and different ways of doing it.
I'm in fact the only juggler stupid enough to use real bone china crockery in any of his shows.
People juggle many different objects in many different ways. Some do it in pairs, or even in threes. Many juggle Indian clubs, whereas others juggle balls, or hoops, or a mixture of things. In this program, we'll be modelling juggling mathematically. To do that, we'll need to restrict the patterns we're trying to model, so we'll only focus on juggling with balls and upwards. So this isn't allowed, and neither is this. And to begin with, we'll look at patterns with only 3 balls. The most basic 3-ball trick is called the cascade. But there are many 3-ball tricks with names that reflect their patterns, names like tennis, the half shower, the shower, and the inverse shower. Some tricks involve elaborate hand movements as well as throwing, as in this one, which is called Mill's Mess. With so many ways of juggling the 3 balls, it's hard to see how to describe the actual patterns systematically. But that's what's challenged mathematician and keen amateur juggler Colin Wright.
Because I am trying to show you what juggling is all about from the point of view of a mathematician. That doesn't mean it won't necessarily be entertaining. I hope it's entertaining at the same time.
Back in 1985, we decided we wanted a dictionary of juggling patterns. Partly this was so that we could then go through a regular practice session and make sure that nothing got lost. We also wanted to have some kind of grading of difficult patterns and easy patterns so that people who were learning could progress through a set sequence. And we realized that there was no sensible way of writing down a description of a juggling pattern.
If we want a mathematical model of juggling patterns, we have to decide exactly what is being modelled. And that means making certain assumptions in formulating the model, assumptions that may be relaxed at a later stage.
When we tried to describe juggling patterns, the problem seemed completely intractable. So we did what is a standard trick in mathematics, which is to look for a simple problem which was closely related. And what we did was we decided to concentrate on just a subset of juggling patterns. And so we came up with a set of restrictions which were basically that we assumed that the hands were full for just half the time, which made things a lot simpler. We also assumed that the hands always took it in turns, and we also assumed that there was a fixed background beat where every throw occurred on a tick of the clock. And in this way, we threw out many of the artistic style of variations of juggling patterns and were left with what we felt was an essence of the juggling patterns, when the balls could be thrown, and in particular when they couldn't be thrown because something else was there at the same time.
So the pattern must be asynchronous. The hands must alternate. That is, take it in turns to hold and throw the balls. Each hand holds one ball exactly half the time. The hands stay fixed, so there are no hand movements other than those needed to throw and catch each ball. Only one ball is to be caught or thrown at a time. And finally, the balls are to be thrown in a regular rhythm. These are our initial modelling assumptions. In fact, we've also identified 2 variables. Firstly, the pattern. The model should work for any that fits the assumptions. And secondly, the number of balls. So are all these patterns essentially the same? Or are there differences? Certainly all these patterns have symmetry, but what about their timing? How many beats does each ball take between throws from either hand? And is this time, the cycle time, the same for 3 balls as for 4 balls, or 5? Well, clearly the cycle time isn't always the same. But why? Let's go back to the 3-ball cascade. We know each ball is in the air for the same length of time, so watch the yellow one. The ball is thrown, then in the air for 2 beats, held for 1 beat, then in the air for 2 beats, held for 1 beat, and so on. There's a continual repeating pattern being traced out from the left hand to the right, and from the right hand to the left. So how many beats long is the basic repeating pattern of the yellow ball? Well, of course, the cycle time for the yellow ball is 3 beats. And the other balls? Well, the pattern is symmetrical. So they too must have a cycle time of 3. And we can describe this basic 3-ball pattern by this time graph. So is this the end of the story? Does the time graph describe the basic 3-ball cascade completely, reflecting all the assumptions? Well, no. One assumption was that their hands alternated, and this time graph doesn't show that. The yellow ball is thrown by the right hand, then caught and thrown by the left hand, then caught and thrown by the right hand, and so on. And this diagram shows how the yellow ball is caught and thrown by alternate hands with a cycle time of 3. And if we add on the paths of the other 2 balls, we get this lovely ribbon pattern representing the basic 3-ball cascade completely. In practice, many jugglers throw the same basic pattern, but vary both the ways that the balls are thrown, throwing some under and some over, and the timings. And because many of the 3-ball patterns have the same cycle time of 3 for each ball, they could all be described by the same ribbon pattern.
And now Anthony's going to attempt something that even the world's greatest jugglers have never achieved. That's an 8-club flash.
Well done. Congratulations, Anthony, a new world's record, flashing 8 clubs.
With the help of our basic assumptions, we've managed to model the simplest possible pattern with 3 balls. So let's change one of the variables. What will happen if the number of balls is increased to 4? Perhaps the first surprise is that for the fountain, the standard 4-ball pattern, the balls are thrown in pairs. Each hand throws 2 balls asynchronously with the other hand. And the cycle time for each ball, watch the yellow ball. Well, of course, the cycle time is 4 beats. And splitting the time graph between the 2 hands gives us this ribbon diagram for the yellow ball. And the ribbon diagram for all 4 balls, well, it's this. This pattern has a cycle time of 4 for each of the 4 balls.
Gene Jones, you're the Guinness juggling expert, aren't you? So we have to ask you, what are the rules for this?
Well, basically, Anthony's going to juggle 7 flaming torches. The difference between a juggle and a flash is that in the juggle you go more than one time around and still catch everything. Here it is, 7 torches.
Oh, hey,
never been done before. Anthony Gatto.
Yeah.
He's done it.
Okay, it may not be a world record, but we have found mathematical ways of describing the standard patterns for 3 balls and for 4. And we found that for 3 balls, each ball was alternately caught and held by different hands. Whereas for 4 balls, pairs of balls are thrown asynchronously by the same hand. So what happens with the standard 5-ball cascade? Well, 5 is an odd number. So 5 balls must be caught and thrown by alternate hands. Why is that? Let's see the ribbon diagram for this 5-ball standard cascade. An odd number of balls means an odd cycle time. Here, as there are 5 balls, that's 5. So to keep within our modelling assumptions, each ball has to be thrown by alternate hands. But here, the number of balls is even, so each ball is caught and thrown by the same hand, with a cycle time of 2. And with 1 ball, well, 1 is odd, so the cycle time is 1, and the ball is passed from one hand to the other without pausing. So in the standard pattern, each ball has the same cycle time, equal to the number of balls being juggled. But the way they're thrown depends on whether that number is odd or even, on its parity. The three-ball cascade is described by the sequence 3, repeated over and over again for each ball. The four-ball pattern by repeating 4 continuously. And the five-ball one by the sequence 5, over and over again. In all the basic patterns, the symmetry means that the order in which the balls are thrown must always be the same. But if the jugglers want to throw any other pattern, then they'll change the throwing order, and in doing so, swap the balls around. Provided these new, more complicated patterns still obey the list of assumptions we started with, juggling mathematicians describe them by repeated sequences of cycle times, using what they call site swap notation.
Each throw, when it's juggled, has to land at a time so that it doesn't clash with any other balls. Now, when you're doing the standard pattern for a given number of balls, each ball is thrown and caught in turn. So if you're juggling 5 balls, each ball is thrown every 5th time. However, you don't have to keep them in strict order. What you can do is exchange the sites at which they land. So you can throw a ball so that it lands a bit late, and then the one that would have landed there can be thrown so that it lands a bit early to fill the gap left by the one before. And so you can exchange the sites where they land. You can swap the sites, and hence the name, site swaps. And these can be described simply by saying how many beats later is this ball next to be thrown. You don't worry about the amount of time it spends in the hand. You don't worry about the actual physical height to which it has to be thrown. You don't even worry about whether it gets bounced off your knee or off the floor or stuck on the table or in your mouth. You only worry about when it has next to be thrown. And so by swapping the balls around in the order, so you can get different variations which require different heights of throws or types of throws in order to get this variation.
Okay, question number 3. What have we done? It says to throw a ball higher, I must give it a greater impulse. Okay, let's have a look. A lot of tricks involve throwing one ball much higher up out of the pattern. Okay, now that needs more impulse. Let's see if you can use your knowledge of impulse to suggest the 2 ways which I could throw a ball higher. Okay? You can tell me 2 ways. Go on then, Mark.
You could throw it for longer, or you could give it a greater force.
Okay, superb. 2 ways of doing it. Either I apply the force for longer, that's lucky, or I can apply a greater force in less time. Impulse is force times time, so either you increase the force or you increase the time. Excellent stuff.
So how are the ideas we've already seen extended to cover harder patterns? What's happening in this pattern? Well, the balls aren't always in the air for the same time, and their throwing order changes too. Yellow, red, violet, then violet, yellow, red, then red, violet, yellow, and so on. So what's the juggler doing to swap them? She throws the first 2 balls higher than usual. Then she swaps the third to the other hand and immediately throws it before the other 2 are caught and thrown, and so on. What's happening here numerically? Each higher ball has a cycle time of 4. Well, as we've seen, swapping from one hand to another means a cycle time of just 1. So this pattern can be described by the finite sequence 4, 4, 1, repeated over and over again. But is there any link between the length of the repeated sequence and the number of balls being juggled? It can't be the number of balls, because for basic sequences it's just one number, a 3 or a 4 or a 5. Whereas in the repeated cycle time sequence for this 3-ball pattern, 4, 5, 1, 4, 1, the length of the sequence is 5. But the average of these cycle times is still 3, the number of balls. And it turns out that the average cycle time must always be the same as the number of balls juggled. So does this mean that if the average cycle time of any sequence is equal to the number of balls, that it can be juggled? Well, no, that's not always enough. And even those sequences that can, in theory, be juggled are not, in practice, always easy to throw. For instance, it isn't easy to throw a cycle time of 2 in the middle of a pattern. This pattern has repeating cycle times of 3, 4 and 2. And this professional juggler has chosen to hold the 2 rather than throw it, allowing her to make patterns like this. In allowing the 2 to be held, we've actually relaxed our original assumption that every hand must hold a ball for exactly half the time. But that's very much a part of any modelling cycle. Having been around the modelling cycle once, we'd always go back, review and possibly amend the assumptions. But if you already know how to juggle the pattern, what's the practical use of being able to write the notation down in numbers?
When we wrote down the sequences of numbers corresponding to the patterns that we knew, we found that there was patterns within the sequences. So there seemed to be gaps. And when we filled the gaps, that then gave us new juggling patterns that we hadn't known before.
And I was lucky enough to be able to demonstrate this revelation myself when it was featured some years ago on Tomorrow's World. What makes some juggles juggleable and others not? It turns out that there's a mathematical structure to the successful juggling sequences. Now, if you plug those into a computer, you can get it to try out every possible juggling sequence with any number of balls. And by watching that, you can work out how to do it. So, for the very first time on British television, we bring you one of the entirely new juggling sequences. So what of the future of juggling? Well, the people at this workshop are combining juggling with dance, choreographing routines, perhaps for a stage performance, but maybe just for fun. And maybe they too will be using some kind of mathematics to describe their routines.
The thing that many people find more interesting in juggling is juggling with more than one person, where you pass things between you. In some ways, an extension of the ordinary sight swap notation already covers that. What really happens is you have both people doing juggling patterns, and at fixed times you make sure that the one that you catch has come from the other person instead of from yourself. So what you can do is write down the pattern that this person is doing and the pattern that this person is doing and say, well, that throw actually is not to yourself but to the other person. And so the question of the exchanges between people is simply an augmentation on top of a pair or triple or more of patterns.
There has been one or two mistakes in this routine, and one of the main mistakes was this club was missing right from the beginning, so we're going to have to do the whole thing again. Oh no! Look, I'm sorry, there's no way around it.
So why do people juggle?
To me, the fun is simply in maintaining the pattern, creating something which you have to work at to hold, and which is perplexing to watch, and which keeps people fascinated in what's going on because they can't quite see it all. And the structure and the spatial arrangement is in the fun. That's the joy of juggling for me, is in creating this thing out of thin air, and then when you stop, you catch all the balls and it's gone.
Every time you get something right, it's a sense of achievement. It's having a goal at the end of the day, or at the end of the week even, or even longer than that. When you do get it, it makes you feel really happy.
You can't think about what you're doing, because you won't be able to do it, but you can't think about anything else, so you have to think about it. And I think that's quite good fun.
When you're juggling like this, you start to think about the mortgage or insurance problems, you just drop them, so it's a great stress reliever.
Well, lucky the table was there, I'd have dropped that one.
Sorry.
Note the silly expression on the face, mandatory for juggling.
With the central government, or with the state governments, or at local authority level. So I think the argument over sovereignty takes a different form, reflecting a very different kind of constitutional history, and therefore raises the temperature in the UK in a way that it doesn't in France or Germany.
And isn't going to go away.
It certainly is not.
Richard, thank you very much. In the next program, we'll be looking at the politics of equal opportunity.
You're watching BBC Learning Zone. On BBC Learning Zone now, a life or death situation for the largest animal that's ever lived, the blue whale.
The Earth is full of life. It supports a great variety of animals. But today, the survival of some species seems uncertain. The threat of extinction hangs over many animals. The great auk was once a common relative of these guillemots and razorbills. But like the notorious dodo, great auks were hunted for food, and now they're extinct. Was this extinction our fault? Might it have happened anyway? After all, human hunting can hardly be blamed for the extinction of the dinosaurs.
Well, extinction's a perfectly natural process, and if you think about it, every species of animal and plant on Earth has either already become extinct or is going to become extinct at some time in the future. And very few of them have a lifespan of more than, say, 3 or 4 million years. Even people will become extinct. What's changed is that people have such a dramatic effect on all these animals and plants through hunting and pollution and lots of other threats, is that we've speeded up this process. And as a result, the rate of extinction has changed dramatically from what people estimate a rate of about one species becoming extinct every 1,000 years to nowadays a rate more like 1,000 species every year. And many of those species are disappearing even before we know they exist.
Every extinction is a loss to us. It's a loss to our spiritual experience. What's more, extinction leads to the loss of a potential resource for our own survival. Even the reduction of a population to a low level can have disastrous consequences for people who depend on them for their livelihood. Overexploitation has caused dramatic reductions in stocks of many types of fish and left too many fishermen unemployed. Depleted fish stocks may recover if left to themselves, but extinction is permanent. Driving other species to extinction can hardly be a viable long-term strategy for the survival of the human race. Hunting for food is an obvious example of the use of animals as a resource for humans and can be a cause of extinction. The great whales are prominent among species where exploitation has led to a reduction in numbers. The largest of all mammals, the blue whale, has suffered particularly.
An average blue whale is almost as long as a Boeing 737, and it weighs the equivalent of the entire population of the Falkland Islands. That's 2,000 people. It's a really big animal, bigger than any of the known dinosaurs, bigger than any other animal on Earth. And in the last 200 or 300 years, we've hunted the blue whale almost to the point of extinction.
The population estimates for this whale suggest that their numbers have fallen from 250,000 to as few as 1,000 in the southern hemisphere. What will become of the blue whale and other endangered species, no one knows for certain. But some people believe they may be able to predict future changes in population. And to do that, they use mathematical models.
Models give us an idea of what to expect. We can go out and measure populations, but unless we can know what the population is today, but we need to be able to project if this happens, then the population will grow. If this happens, the population will decline. And all those things are based on models.
Such models may be complex, taking into account many details of species biology and behavior. But they can build on simple beginnings. The factors that change the numbers in a population are births and deaths. Each of these depend on the current size of the population. Suppose that the number of deaths each year is a fixed proportion of the population, say 10%. If the population is 2,000, then there'll be 200 deaths each year. But if the population is twice as large, there'll be twice as many deaths. In general, we might model the relationship between deaths and population size by a graph, like this. The straight line is appropriate if deaths are a fixed percentage of population size. That seems feasible, but what about births? How might the birth rate be related to the population size? For these guillemots, the more birds there are, the more births we expect. But if numbers are very low, they may lose all their young to predators. And if numbers are high, they may run out of space for nests. What does this say about a graph of births against population? If the population is very small, there are no births. As the population gets bigger, so does the number of births. But the birth rate doesn't increase as fast as the population. Competition for resources reduces the birth rate as a percentage of the population, so the graph flattens out. That sounds fine, but is this pattern of births valid for whale populations?
These animals range throughout the world's oceans, so you could have lots of whales, but they're not encountering each other frequently enough to reproduce.
I mean, it's hard enough for a person to find a blue whale in a vast expanse of ocean, but for another blue whale to find one and to mate and so on is also very difficult.
So our graph of births does correspond to what we know about whales. In fact, it corresponds to observed data on many species. We can use these graphs of births and deaths as a mathematical model. The aim of this model will be to decide whether a species may survive. But to do that, we must look into the future.
It's considerably easier to use a mathematical model to look back at what you think has happened and you have some check over it. It's considerably more difficult to extrapolate into the future because a model of necessity requires parameters, and some of those parameters it's very difficult to predict.
How might we use our ideas about births and deaths to look into the future? Let's look at both graphs together. The predicted future depends on where we are now. If the population is this size, then births and deaths are in exact balance, and the population should stay the same. And the same will happen if the population is this size. If the population is this size, then there are fewer deaths than births, and it will increase. While if the population is this size, there are fewer births than deaths, and the population will decrease. Either way, the population size moves towards this level, which we call the equilibrium level. If the population is anywhere in this region, there will be fewer deaths than births, and the population will increase towards the equilibrium level. But what happens if the population is very small? Let's look closer at this area. There are fewer births than deaths, and the population will decrease to extinction. This point shows the minimum sustainable population. If the numbers are above this level, they can recover. Below it, extinction will follow. So this minimum level is critical. To save any threatened species, we need to take effective conservation measures before the population falls below that minimum sustainable level. Barnacle geese that winter in the Solway Firth in Scotland suffered exploitation for food during the war years, and in the 1950s were reduced to just a few hundred birds. The creation of reserves for these geese ensured their protection from hunters. As a result, their numbers recovered to over 12,000 by the 1990s. Such a recovery in numbers is one of the possible futures predicted by our model. We can show our model's predictions with graphs of population against time. This is the equilibrium level for the population. The future depends on current numbers, but generally the population will tend to settle at the equilibrium level. Hunting may reduce a population below this equilibrium. Left to itself, the species can recover its numbers, but only if it has not been reduced below this level. Once below this, the population is on the road to extinction. Even if a population is recovering, the time taken varies enormously. Some species can increase their numbers very rapidly. But whales have very low birth rates, and it takes a long time for a whale population to recover its numbers. For any population whose numbers are dangerously low, the key for their survival is a very simple one. Is it any longer possible to sustain a birth rate that is greater than its death rate? One possible source of death is hunting. So far, we haven't considered this in our model. For a threatened species, any hunting, however slight, may tilt the balance, so that deaths exceed births. Is this the case for blue whales? After all, it was whaling that reduced their numbers originally.
The blue whale is the largest species of animal ever to have existed on the Earth. It can weigh up to 190 tons, be 100 feet long. You would expect it would have been one of the first targets of the whalers. But in fact, the blue whale is a very fast-swimming whale, and it wasn't until the invention of steam-powered catcher boats and the explosive harpoon that whalers were able to turn their attention to the blue whale.
After World War I and before World War II, there was a major harvest of blue whales, and the world's populations were brought down considerably. During World War II, there was no whaling, and so there was a period of ability for whales to slowly recover a little bit. And then after World War II and into the 50s is when the whale populations were really brought to their lowest levels.
It's a very sad history. Blue whales were attacked very, very severely. In one season they took over 30,000 animals in the southern hemisphere alone. And of course the whale stocks couldn't withstand that.
Because of its large size, hunting of blue whales was merciless. Concern about the effects of uncontrolled hunting led the whaling nations to come together and form the International Whaling Commission.
The history, if you like, of whale management began in a very crude way with the establishment of the International Whaling Commission. People knew that they might catch too many whales. Originally, all that you could do was wait for the population to crash. The catches effectively would drop off to such very low levels that anybody would be able to tell the population was in trouble, and then you stop the fishery.
It soon became obvious to the IWC that if they were to continue exploiting whales, they would have to devise ways of preserving the stocks. Originally, they set quotas on annual whale catches. Theoretically, the optimum quota was the maximum sustainable yield, the largest annual catch achievable on a continuing basis. But what does that really mean? Looking back at our graphs, hunting will increase the number of deaths. If the annual catch size is the same whatever the present population, then the deaths graph is moved up by the number caught. With deaths increased by hunting, what's the future for the population? If the catch is very high, then whatever the current population size may be, deaths will exceed births, and extinction will follow. However, suppose that a smaller catch is taken and that numbers are high to start with. Then the population will settle here, and there'll only be a small reduction of the population below its equilibrium level. Catches in this region can give sustainable yields, not leading to extinction. If a quota is set to keep catches at this sort of level, then all would seem to be well. But there are problems.
The whole whaling issue, really since the Second World War, has been based on quotas. And there's a tremendous difference in the number of whales people think there are that exist. And so when we hear that people aren't, let alone sticking to quotas which are controversial, they're actually taking more than that, it's very frightening.
The Commission as a political body can establish a catch limit, but of course what really matters in terms of both our model being able to predict things is that the catch limits are kept. Now that can be a difficult thing to ensure depending on the type of operation. If it's a small operation with hundreds of individual whalers in small boats, it's rather difficult to police. If it's a single factory ship, then it should be relatively easy to police.
It's natural for whalers to seek to have catches that are as high as possible. This will continue while the population seems unaffected by hunting. However, our model predicts a relationship between catch and population size. Any increase in catch reduces the population size, but not dramatically. Even when we reach this point, the population size still looks healthy. This is when the catch has its largest sustainable value. But if the catch is above this level by the least amount, then the population will inevitably become extinct. With population related to catch like this, it will never look seriously overexploited until the point of no return has been reached. With such a precarious balance, setting and keeping to quotas that really are sustainable may be politically impossible. Our model shows that any attempt to control whaling
introduced a commercial whaling moratorium, or pause in whaling as it was called, to take effect from 1985, 1986. Now, one of the things that the Scientific Committee was asked to do in that period was to comprehensively assess whale stocks, and that was in the light of management procedures. So we had quite a major task in the Scientific Committee to look more or less from scratch at the question of whale management.
Never intended as a permanent state of affairs, The ban on whaling allowed whale populations to recover slightly, and the scientific committee of the IWC to come up with a revised management plan.
Then began a biologically relevant management where they managed each population based on the number of individuals they thought were there, how fast they thought the population could grow, and from this they got an estimate of the number of individuals that could be taken each year, that it wouldn't create a negative growth in the population.
The revised management procedure is a result of our ability to use mathematical models. It allows us to try things out, see if they work out which parameters are important and which aren't, in a way that we could not do merely by observation of the animals in the ocean.
But what of the blue whale? Have we taken this creature beyond its point of no return? One key issue concerns their current numbers. Are they above or below the danger level? And can they recover?
No one really knows how many there were at the beginning of the century, but it was probably in the hundreds of thousands. And we've hunted so many, we've killed so many, that there are estimated to be between 6,000 and 14,000 left, that's all.
On the 6th of December 1994, the Antarctic sanctuary proposed by the French government became a legal reality. This haven for whales, long awaited by conservationists, would seem to be the respite needed by the blue whale. But is it? Not everyone is equally enthusiastic.
The issue becomes whether or not the member nations of the IWC will honor the sanctuary. The nations that think it's a good idea are the ones that are currently not whaling. The ones that don't think it's a good idea, Norway, Iceland, Japan, will probably continue to whale, or at least will try and either leave the IWC or protest and maybe bring about the demise of the Antarctic sanctuary.
There are perhaps two schools of thought in terms of the Antarctic sanctuary from a scientific point of view. The first school of thought would say that however carefully we may have tried to devise a safe management procedure, however many different levels of uncertainty we've taken into account, you can never be 100% sure in the real world that something else isn't going to happen. The only real way to take that into account is to ban whaling, is to have a sanctuary. The other school of thought says that the revised management procedure has been tried and tested for almost everything people can think of, plus a few things people would not even dream were likely to happen. In such case, it would not allow catches on depleted stocks. It would only allow catches on those species which were able to sustain that level of exploitation, in which case there's no need to have a general sanctuary. Essentially, you have a sanctuary for each individual species should it require one.
However, there are those that feel that mathematics must not stand apart from the moral issues around whaling.
A whaler once said that if whales could scream, there'd be no whaling because nobody could stand the sound of it. The pain must be so intense. And so I feel that what we should do is absolutely forget all of these calculations and stop whaling altogether.
It's a matter of opinion whether we must stop whaling completely to avoid disaster. What is clear is that large-scale hunting of animal populations requires scientific study. Quantitative methods are one vital tool in predicting the effect of different exploitation patterns. Mathematics can predict problems and help to design procedures to avoid them. What it doesn't do is answer the moral question of whether any whaling can be justified. Neither can it provide the political will to ensure that rational policies are put into effect.
If you'd like to know more about BBC Learning Zone, you can write to BBC
of Ideology.
This is BBC Learning Zone. On BBC Learning Zone now, the OU tells the story of a very successful mathematical mistake.
I'm a mathematician. About 7 years ago, I left the Georgia Institute of Technology to found a company. The work that all of the employees are engaged in derives from a mathematical theorem. The work that they do will potentially influence the way you look at pictures on television in the future.
This is the story of 100 years of maths research, leading to a very profitable application, but starting with an intriguing mistake by one of the world's greatest mathematicians.
This is the Mittag-Leffler Institute in Stockholm, and this is really where our story starts. In 1884, the King of Sweden and Norway, Oscar II, asked the Swedish professor of mathematics, Gösta Mittag-Leffler, whose beautiful house this is, to organise a mathematical competition for him to celebrate the King's 60th birthday in 1889. One of the questions they wanted to resolve was whether it was possible to prove mathematically the stability of the solar system. We know from observations that the planets will continue to move in the way that they always have done for a long time into the future. But it's another thing to know that they will always move in that way. And this was the question that they really wanted an answer to. And one of the entrants to this competition was the brilliant young French mathematician, Henri Poincaré.
Well, Poincaré is without doubt one of the leading mathematicians of all time. He's known as the last universalist. That means he was the last mathematician who really understood pretty much the whole subject. It's just got too big since then. And so he's not going to try for a prize unless it's really important.
It might seem obvious that the heavenly bodies behave in a stable and predictable way, but King Oscar's prize offered mathematicians a chance to prove it.
Now, before Poincaré, people knew about the motion of two bodies. They go round and round each other in ellipses, rather like this. Poincaré wanted to know what would happen if there were lots more bodies. And he focused in on three bodies. Now, that's a bit like we have here, only here we have three magnets, two of which are actually fixed. So the question is not just, if I let go, what will it do? The question is, what can we prove about it mathematically in general?
Poincaré showed that in one situation there are indeed periodic solutions, which give repeating patterns of movement that remain stable over time. However, although Poincaré brought new skills and vision to this problem, it turns out that he didn't get it all right the first time.
Like many mathematicians, I came here to do some research, to take advantage of these wonderful libraries and all the marvellous books that are here. In fact, I think it's probably true to say that this is the best source for 19th century mathematics anywhere in the world. In particular, I came to search for information concerning Poincaré's winning entry. It seemed to me there was rather a mystery about it, and I really wanted to find out. One of the things that Poincaré was very bad at was actually drawing. In fact, as a student, he got 0 for his drawing exam, which meant he almost failed to qualify to graduate. But he was so brilliant in everything else that it was sort of allowed to go through. When I eventually found the Poincaré cupboard, I discovered that in fact Poincaré had won the prize for a memoir that contained a very grave mistake. There was the published version, which appears like this. And then there was the original version, which, although printed, which was this version, was never actually published. We can see corrections here and pages of notes written by him.
Poincaré actually was a bit sloppy, and so it's not surprising he made a mistake. But he was also very, very quick, and he was really thinking hard about the problem, so it's also not surprising that he noticed the mistake while everybody else was still working their way through this very, very difficult piece of work. So they probably only got to page 2 or 3.
And in looking through this very carefully and seeing the corrections that Poincaré had made, I discovered what the root of the mathematical problem was. Poincaré originally thought that the solutions that he had found were well ordered, and in fact it turned out that when he discovered the mistake, they were not well ordered at all.
What's so unusual about Poincaré's second solution is that unlike the previous solutions, which are periodic, his solution is all over the place in a very irregular, almost random looking way. But you know there's nothing random in the equations. And very, very tiny changes in the position of the planets lead to very big changes later on. So 100 years ago, Poincaré had discovered what nowadays we call chaos.
Poincaré was completely horrified at his discovery of this mistake. And this was not just because of having made a mistake, and he was embarrassed almost at having won a prize for a memoir that contained a mistake, but also because it meant that his original view, his conception of the world, if you like, had almost been turned upside down, because these solutions that he had found, which he had thought were well ordered, were in fact chaotic.
This completely changed the old worldview of a clockwork universe, running along predestined lines, obeying immutable laws, always predictable, always doing the same kind of thing. Instead, what we see is a chaotic universe. It's obeying laws, they're very simple mathematically, but the behaviour is random, it's unpredictable, and it's very, very complex.
Henri Poincaré was able to discover chaos because of his unique ability to visualize extremely complex and evolving mathematical problems.
This is the kind of thing that Poincaré would be faced with, some mathematical rule that you have to keep repeating over and over again. For example, here, x might be the position of a planet at a given instant of time. Of course, Poincaré's equations are going to be much more difficult than this one. And what you have to do is say, well, suppose we start with some value of x, let's say 1.5. Then what happens when you calculate the formula? Well, in this case, we actually get 3.5. And then take the 3.5, plug that in at the front, do the calculation again, and carry on repeating that. This is a process called iteration, and get the whole sequence of movements of the planet. The problem is you need tens of thousands, hundreds of thousands, maybe millions of these calculations. And with pencil and paper or with a blackboard, there just is not time to do it. So the obvious way is to do it on the computer instead. What I'm going to do here is look at a more complicated set of equations. And firstly, let's assume you're an old-fashioned mathematician who can only do 100 calculations before he runs out of steam. So what he would see is this. He would see a curve and it stops and it doesn't seem to go anywhere. But suppose we had the computing power to do 10,000. Now the full glory of the thing becomes clear. Now this particular attractor, as it's called, was discovered only in the 1960s, and it was only discovered then because that was when the computing power first arose for doing this kind of thing.
The process of iteration can often produce weird and wonderful shapes. The French mathematician Benoit Mandelbrot called them fractals because they have a strange property called fractional dimension.
Julia discovered these back in the early part of this century, but they weren't plotted until the late 70s, early 80s, when people had personal computers. Now, if you look at this set, it's called a seahorse because, as you can see, small tails are repeated all over the picture at different scales. And we call this set a fractal.
I first got involved when I saw some computer drawings, which were the first attempts to actually draw this particular kind of fractal. This particular kind of fractal had actually been known as a theoretical possibility since the time of Poincaré, but nobody had actually tried to draw them. And seeing these beautiful pictures brought the whole subject to life. And these patterns are formed by giving the computer a very, very small amount of input data and then getting it to repeat the same simple operations over and over again. This is what mathematicians call iteration. And what you can see happens is that you get similar structure in the patterns occurring at all different parts of the picture. Like, for example, these angles here occur in many different places, and if we were able to magnify, you would see yet smaller circles with the same angles in between them. So the same pattern is repeated in many different ways, forming this very complicated picture.
Mathematicians have found these new amazing creatures that lived inside computers, and they wanted to understand them. So it was like an explorer who'd just blundered into a new continent. And so they wanted to find more of them, take a good close look at them, arrange them into families and understand how they're related to each other.
In fact, fractals have been known about as mathematical objects for a very long time, but they were regarded, right up to the time when I was a student, they were regarded as some sort of weird monstrosities, nothing to do with reality at all. When you look around you at nature, at objects like trees and clouds, it's very suggestive to think that they're in fractal forms. For example, supposing that we look at the leaf of this fern, you can see the self-similar structure repeating here. You see, along here you get one pattern, and then these fronds on the side are very closely repeating the same bigger pattern, but at a smaller scale and with many repetitions. And then on the edges of each of these fronds, you see again the little divisions into shapes which yet again are similar to the shapes that we started with. This leads me and other people to think that actually there is something very fundamental about the geometry of fractals which could be very important in the study of nature. And I think it's very important, therefore, that we learn to really handle the right kind of mathematics.
Not a real plant, but a mathematical fractal known as Barnsley's fern. It shows one of the key properties of fractals, self-similarity. The fern looks as if it's made up of small copies of itself. For example, the fern can be transformed, rotating it and making it smaller, and then another transformation sliding it to the right to give a similar version of the fern at this new scale. In fact, the whole fern is generated by a simple set of mathematical transformations. Mathematicians call them affine transformations.
A lot of people are convinced that fractals are the true geometry of nature. Classical geometry with cubes and spheres and things like that just doesn't look like the natural world. But if you look out of the window, you see things like trees, mountains, clouds, and they have a kind of fractal repeating structure. They have structure on many scales, just like a fractal.
Well, speaking as a pure mathematician, the important thing is that a subject should have beauty, elegance, structure, and also lead to interesting and difficult problems. I mean, some of the problems associated with fractals, it's taking people decades to solve. There may or may not be applications. The key thing is that people would do this even if there were no applications.
Well, I find these pictures visually very, very attractive. But the main thing is that behind them there's a tremendously rich amount of mathematical structure. And I just really enjoy pitting my brains against trying to understand all the relationships between things and prove things and calculate things that nobody's ever been able to calculate before. I think that's enough.
Different mathematicians have very different attitudes to research. Some of them do it simply because there's an interesting problem, they can do their mathematics, they want to know what it's like, and they get involved in the problem for its own sake. Others, at the other end of the spectrum, will only work on a problem if they can see real practical payoff.
It's almost like it would be strange to be a poet and never read your poems to anyone.
Michael Barnsley is an English mathematician who now runs a multi-million-dollar company in Atlanta, Georgia. He exploits fractals, simple equations producing complicated pictures, by turning this idea on its head.
Well, some people hope that just as here we see complex behaviour generated by very simple rules, and as in fractals we see complex pictures generated by very simple rules, that it would be possible to take a very complicated picture and work backwards to the simple rules that capture that complexity.
Well, the problem is that if you take a single picture and you put it in a computer, it occupies an awful lot of space. For example, the amount of pictures required for 1 second of video would take the same space as one whole fat telephone book with 2,000 pages. So you've really got a problem if you want to send video over phone lines, for example. Just imagine how many telephone books. You'd have to send 60 telephone books worth every minute. And if you've ever tried faxing documents over phone lines, it goes much slower than a telephone book every second. So there's a problem. And the problem is, instead of sending all of that space, you just want to send a little bit of it, that sort of amount, so that you could reconstruct the whole telephone book from the little bit of space. Or to put it another way, you could reconstruct each picture from a little bit of information. You could recreate the picture back again. And the way we do that is using the theory of chaos and fractals. Now, over here we've got a picture, guess of who? Henri Poincaré. And what we've done is we've already digitized him, and we've set the fractal compression system to work on the picture. David, can you show us how this picture is broken up like this?
So the fractal compressor has split this image into many thousands of small squares. For each of those small bits, it's found a bigger bit elsewhere in the picture that it can transform and make look like the small bit. The compression comes by sending only the transformations between the bits and not the information that's in the bits themselves. This sort of gives a recipe for a way to make Poincaré.
To get an idea of the fractal compression method, look at the bridge of Poincaré's nose. If we break it up into smaller squares, then it turns out that there are only 4 key patterns. Now we search for larger pieces of the picture, which are similar to our small key patterns. For example, this large square rotated through 90 degrees, shrunk and moved over, matches this smaller square. In fact, every small piece of this picture can be matched onto one of the 4 larger pieces by these transformations.
Here's an example of a block in the corner of one of the postcards in the background that matches with a bit of his coat. The interesting thing here is that this is really quite a dark square, and the darker part is on the bottom, but in the red square it's a much lighter square, and the darker part is on the right side. So the green square has been rotated, and then it's had its brightness and contrast adjusted the same way you adjust the knobs on a television set, so that although this is quite dark, its variation is the same as the lighter variation that you see here, and it's been twisted through 180 degrees. Here's a place where the computer has made a match between a bit of Poincaré's hair and a distorted piece of his wallpaper, and this green square will be distorted and mapped into the red square you see on his head.
The remarkable thing is that you only need to have a list of those transformations in order to reconstruct the whole picture. If you apply their equations repeatedly, then after just a few iterations, the picture's indistinguishable from the original.
So a CD-ROM only holds about 600 megabytes of data, which means that if it was not compressed, it'd only hold a few minutes at most of video. So what happened was Microsoft wanted to put numerous pictures, color photographs, onto a multimedia encyclopedia called Encarta. They actually compressed 7,000 color photographs, all as fractals. No one knows it. When they look at the pictures, they just think they look like photographs. They're really looking at fractals. Whatever you see, anywhere, anytime, any place ever, you will see more of it in that same picture. And that each picture is fundamentally different. I can see in front of me an orange rock, and goodness me, I never sat here before, I never looked at this rock, but big pieces of it look like smaller pieces. Again, I look and I see the trees behind me, and there's not a little strange, isolated, existential leaf in the air all on its own. There are tens of thousands of leaves, and they're all of different sizes. It's as though they are trying to obey a rule or a law of nature, the rule of affine redundancy in real-world images. It's that affine repetition that we exploit by the mathematical theorem that is used in fractal image compression. It counts on the fact that in the picture you are going to, whatever is in a picture, there is going to be more of it at different scales. And the strange thing is, that's exactly the property that mathematical fractals have. So if I pretend that what I see out here was a giant fractal, and I just forget that it's the real world for a moment, and I say, as a mathematician, how would I find the formula for that fractal? Well, that's the problem that we solved.
It's great to see this area of pure mathematics, which has been going for almost 100 years, really without any view to applications, unexpectedly producing an application which might affect everybody's lives.
I think that to predict the course of mathematical research, you would have to be some sort of genius, even better than Poincaré. In other words, I think it's a jolly difficult thing to do. In fact, the most unexpected things that seem at the time quite useless turn out to be absolutely fundamental.
Well, some of the things that have clearly influenced the development of mathematics over the last century have been computers, visual imagery, and interactions with nature. But much more important than that, the rogue element is human imagination. And it's that which is completely unpredictable, and that's what makes research so exciting.
Yes, I think so. Bias tends to imply that something is distorted, deliberately, consciously distorted. If you like, bias is a form of propaganda. Now, sometimes ideology may well take that form at crucial historical political moments. But by and large, I think we're dealing with a broader spectrum of unconscious influences and less conscious, deliberate influences on ideas.
That's all we have time for. Greg, thanks very much indeed. Well, the next program in the series is TV10. Like this program, it also looks at aspects of identity and identification, specifically questions of national identity.
Right, thank you, everybody.
Yes, please.
Thanks, Joe. Should we keep that?
I'll do it. No, I'll go and get it.
How's it going anyhow? Not so bad.
Music, movement and maths on BBC Learning Zone now, a language for movement.
Many movements are spontaneous. They occur naturally, without conscious thought. Other actions are more controlled. They don't just happen. There's a deliberate intention behind them. Some sequences of movement are improvised, made up by their performer as they go along.
Okay, come on.
But many sequences of movement are designed, worked out in advance by their creator, who intends them to be repeated in exactly the same way, on different occasions and by different people. These choreographed sequences can only be recreated accurately over and over again, whatever the time interval between performances, if the movements are analyzed and recorded. If there is a language for movement. But would the ability to analyze our movements be of any use to most of us?
If we grow up really unaware of how our body moves, how we can use our body, how we can adapt the body to many different activities, then maybe we can achieve all that's necessary intuitively or just by an innate sense. But I claim there's a value in studying and being disciplined about an understanding of what all the possibilities of movement are.
Warren Lamb worked closely with Rudolf Laban, a major advocate of movement analysis. Together, during the 1940s and early 1950s, they observed and recorded the actions of factory workers using Laban's own notation. This is a record from a tile factory. But the way individual operators carried out each stage in making a tile varied.
There were operators who were doing this all day long, but they all did a little bit differently. One person might sort of approach the sand with a rather slow movement and then do it quickly. Another might approach it more from above. Another one might sort of go much more roundabout to do it. And the traditional time and motion study at that time always wanted to reduce the action to the absolute minimum. Laban said, no, you must, so long as the operator does the essential things, then the operator must find his or her own rhythm, and by that means will avoid stress, and it will benefit the company because production will increase.
Always very interested in mathematical ideas, Rudolf Laban devoted a large part of his life to the description of movement, both symbolically and geometrically. Both his symbolic language and his use of geometric forms arose out of his lifelong involvement with dance.
In a sense, we are all dancers, and we are all moving in a particular form or pattern. So it's not dance, of course, in the sense of a theatre presentation, but it is dance in the sense that we all employ rhythmic movement, and we all use different rhythms.
If this dance, or any dance, is to be recreated, to be performed over and over again in exactly the same way, then every movement of the dancers must somehow be remembered. As with recording mathematical thinking, one way of recording decisions about how the dancers move is to write it down, using a designed and structured language, to use a symbolic notation. And all written notations record by encoding. However, if a record is to be of any use, to be the basis for recreating a dance, the coded symbols need to be decoded, to be understood by others. So it's not the symbols themselves that are important, but whether they can be deciphered. The ballet, Afternoon of a Faun, is the story of the love of the faun, a mythical creature, half man, half goat, for a nymph. Both choreographed and danced by Nijinsky, its first performance in Paris in 1912 caused scandal and outrage.
If you think that when they were been performed first time in London, English public thought that they were barbaric, and then when I performed it with Royal Ballet and Grigorievich and Rishova and Ashton insisted that steps should be exactly as they used to be, and the production collapsed because it was too tame.
But has the ballet really become tame? Well, perhaps. Although Nijinsky did write down the movements of the dancers, he used his own notation. And unfortunately, no one could interpret it, because nobody had a key to the meanings of his symbols. So the dance movements were passed on from memory, by word of mouth. Inevitably, movements danced in contemporary productions can no longer be true to the original. No longer those danced by Nijinsky. The ballet has indeed lost much of its original impact. Afternoon of a Faun is a complex ballet of movements involving every part of each dancer's body, and so any record needs to be very detailed. But that's not always as important. This gavotte was first danced in ballrooms in the 18th century. We can be fairly confident that this 20th century recreation is similar to the original, because when he created it in 1720, Kellum Tomlinson wrote down the basic steps using an established language called Fourier's notation, a notation that we can still understand today. When using any dance notation, the challenge is to represent dynamic movement by what is essentially a static and symbolic form, and to decide what to include and what to ignore. This record is largely a floor plan. It shows both where and how the dancers' feet are to move. These dancers are able to go from the symbols to the movements because they know what each symbol means and how they're combined. However, the notation didn't record everything. For example, head and arm movements were ignored. They were left to the performers to provide. There are over 100 dance notations, though, each using different symbols. and each focusing in different ways on the movements they describe. And here are the movements of this gavotte, written down in 3 of the most used 20th century languages of movement. In Benesch notation, which is read, like music, across the page. In Eshkol-Wachmann notation, also written across the page. And in Laban notation, which is written up the page as the dance proceeds. All 3 notations have things in common. Like music notation, each is divided up into bars. And when they're written down, what is produced is always a kind of graph, one of movement against time. Yet there are also differences. By using different symbols and clusters of symbols for the same movements, each notation places emphasis on slightly different things. In practice, the choice of notation is often based not on who can write it, but on who can read, understand, and above all, interpret what is written. Like any language, the major influence on choice is that of communication. Like many dance companies, the Royal Ballet have standardized on Benesch notation, which Joan Benesch, a dancer with the Sadler's Wells Ballet Company, and her mathematician husband Rudolf, published in 1956. Here, one of the Royal Ballet's choreographers, David Bintley, is working on his latest ballet with notator Grant Coyle. Notators, also called choreologists, have been on the staff of the Royal Ballet since 1960, both looking after existing works and, as here, helping to create new ones.
I remember my own pieces, of course, and I remember them when I'm creating them because I'm thinking about them the whole time. And also, it doesn't take me long once my memory's been jogged to get back into a piece so that I remember why I did that and why I did that. If somebody introduces an error into it, I can see it very, very easily. But it is a fact that after I've done a piece, I really kind of mentally erase it. I'm on to the next. When I set a piece, sometimes what is written in the score is never done.
Recently, when I went to America with David and we set a ballet, we did work with a company who had never used choreologists. Their reaction was one of amazement, and mainly because that they just, first of all, couldn't understand how movement could be written down, and then secondly, how well the system worked in the studio, how efficient it was.
If I have a 30-minute ballet to do, and I have to get the bulk of it together in 3 weeks, you tend to kind of throw it down. And where my memory is short, and where the memory of everybody except the notator is short, is when you come back 3 weeks later. And it's a small thing. It could be in the middle of a complex lift that X-dancer actually had his hand here instead of here. And that kind of thing is what I wouldn't see, because my intention is to get the overall effect of the lift. So I know what it's supposed to look like. The notator will be looking at all these things, and he'll be able to tell a dancer exactly where that hand should be. And that, I think, is almost as important as having the thing for the record, is that day-to-day kind of help, and just reminding you what you did 2 days ago.
Nowadays, whatever the dance form, choreographers are rarely alone when they create new dances. Every movement is recorded by a notator, who works alongside the choreographer during the rehearsals for the first performance of the new work.
3, 4, up!
Like the Royal Ballet, here at Kokuma, there's a close working relationship between the choreographer and the notator. And though here the notator is using Laban notation, the process of recording movements is the same. So when does their collaboration begin?
In terms of the notation process itself, it's better to begin when the person that's doing the creating is actually beginning their work. During that period, they're usually working much more slowly. They're going through thought processes. They are using vocabulary as well as their bodies, so that you're much more able to get what the choreographer in this case wants, the choreographic intent. Now, we know that part of that has to do with being one step removed from the choreography, but during that kind of process, you're more likely to get what the choreographer wants rather than what the dancer does.
While the choreographer works out the movements of the new dance, the notator watches, recording the key aspects of how each dancer moves.
1, 2, up.
As his ideas evolve, this choreographer will often refer back to the notator's record, maybe to remind himself about what he's just decided, or to refresh his memory about decisions he made some time ago. And whatever the origins of any dance form, any of them can be recorded and so recreated with the use of notation.
I'm using it primarily with African people's dance. I see it as a way in of understanding that dance first and foremost. Many African people's dance choreographers will say the notation doesn't take on board everything that they want to do. For example, if they're doing a movement in which the spirit enters the body, they will say, but you can't notate that. And I will say, no, but you can't notate it either. I mean, you can't notate something you can't see, but what you can see is how the spirit has acted upon the body, and that's where the efforts become very, very important. Movements such as we saw today, where you have the vibratory movements, movements that shake, these are movements that come from the inside out rather than from the outside in. So you might have a spatial orientation, but that spatial orientation becomes much more meaningful if we're talking about something that involves what we might call flow fluctuations in the body.
There are strong similarities between the ways that many symbolic dance languages work. So to give you an insight, we'll examine Laban notation, the notation Jean Johnson-Jones uses, in more detail. Written in waltz time, this dance sequence can be described like this. But what does each symbol mean? And how are they strung together in a sequence? What exactly is Laban notation?
Laban notation is a way of reading, writing, and communicating movement. Unlike music, Laban notation is read vertically from the bottom of a 3-line staff up. The center line of the staff represents the center line of the body, and it's written from the performer's point of view, so everything to the right of the center line represents the right line of the body, the right side, and likewise the left side. The direction of movement is based on the rectangle. How that's modified will show you which direction you're traveling in space. A symbol with a chimney on top would represent going forward, reversed going backwards. A triangle pointing to the right would represent right, and reverse to the left. The diagonal directions have a point indicating which direction they're going toward. The shading of the symbol represents which level or height that a movement is made in. If the symbol is completely blacked out, it would be a low level. If it was a support, that would represent a plie or bent knees. A symbol with a dot in the middle represents a middle level or normal. Legs would be straight if you were supporting. A symbol with diagonal lines running through it would represent a high level. So supporting it, you would be in releve or up on your toes. The length of the symbol represents the timing. So a shorter indication represents a smaller amount of time. A longer indication represents a longer amount of time. And depending upon where the symbol is placed on the staff, will give the performer the information of what part of the body is moving.
And here's the Laban notation for the rest of this movement sequence. But the important test of any notation is whether it can be decoded, whether the original dance can be recreated from the symbolic record time and time again. During the 1980s, some 70 years after its first performance, a key was discovered to Nijinsky's notation of his Afternoon of a Faun, and a faithful recreation of the original ballet translated into Laban notation.
His score that he had written himself of his first ballet, Afternoon of a Faun, was in the British Library, but nobody could read it. A German colleague named Claudia Jeschke had also got involved with this project, so we met, decided to work together, and by pooling our information and resources, gradually we were able to find out, because there were a few other related materials which we found, to break the code and translate into Laban notation every detail in Nijinsky's score. And what we were able to revive was his ballet as he wrote it down. And it's a beautiful work, much more delicate and sensitive than the memory-based version which one so often sees.
Rudolf Laban was not only interested in symbolic systems, but also in mathematical structure. In addition to designing the symbolic language that bears his name, he relied heavily on geometry as a way of describing movements of the human body in space. He was a talented artist, and his drawings reflect his joint interest in both mathematics and dance. And Laban made use of his spatial ideas to create these dance movements.
His spatial ideas had to do with using various geometric forms, and he identified a number of forms such as the icosahedron, the cube. He identified the diagonal planes that we use in regard to movement in various ways. In relationship to those various forms, he also developed scales, and these scales were combinations of space, combinations of effort, and combinations of time, used in a particular kind of a way.
His so-called scales were a series of dance exercises written to be performed within the 5 geometric shapes known as the Platonic or regular solids. Each regular solid has every edge the same length, and every corner and face identical to every other one. The faces of the triangular pyramid, the tetrahedron, the octahedron, and the icosahedron are all equilateral triangles. There's just one regular solid with square faces, the cube. And finally, one made from regular pentagons, the 12-faced dodecahedron. And in this particular scale, Laban has identified 3 perpendicular planes within the cube. However, the ideal space for a dancer to move within would be a sphere. And the regular solid that's closest to a sphere is this one. It's the 20-faced icosahedron. The variety of ways in which the human body is able to move can be described by using one of the languages for movement. A language with mathematical features, perhaps drawing on geometry as a way of describing how people move, or using symbols to represent those movements. However, ultimately, it's not the choice of language that really matters. Above all, as with all mathematical thinking, it is whether the recorded message conveyed by the symbols can be understood and acted upon by others.
If you'd like to know more about BBC Learning Zone, you can telephone the BBC Education Information Line on 0181 746 1111 or write to room G420.
It's proving to be at the expense often of the consumer. Yeah. It certainly is in soccer. I don't know exactly what the situation is in athletics, but I know big money's coming into athletics.
Well, we've just gone bankrupt.
Precisely my point. This is precisely my point. Now, if that was to happen to soccer, heaven knows what would come.
Dick Tracy, couldn't you spot Murdoch doing this when, Lady Thatcher handed him the franchise?
Well, he hadn't developed so far down the track, but I mean, the fact is that these sports say that they need the money. I mean, athletics, as Roger says, is going bust as a result, but football can see that they may be able to cut an even better deal for themselves if they set up their own channel, and that, it seems to me, and the analysts in the city seem to believe that is the way forward for football clubs.
That's it for tonight. That's it for tonight. Just time to thank my guests, Garth Crooks, Dick Tracy, Kate Hoey and Roger Black. On Monday, that Task Force Supremo, David Miller himself, will be back in this chair. I'll be back next Thursday. Join me then. Good night.
This is BBC Learning Zone with education through the night. This is the look of tonight's programmes. In a moment, the Open University. Then at 2, it's FETV, followed by languages at 4. Teacher training is at 5. And finally, more from the Open University at 5:45. On the menu in half an hour, a look back to last year's general election. Was it really a turning point in British political history? Find out at 1 o'clock. After that, 18th century philosopher Jean-Jacques Rousseau's theories on human nature are put to the test in modern-day South Africa. Democracy in the making at 1:30. First, BBC Learning Zone stays in the most unusual hotel ever, one that is always full but still manages to take in guests. Settle back and discover the secrets behind the strange goings-on at Hotel Hilbert.
Tracking the point at infinity, Max. Tracking the point at infinity. No, left an inch, Max. No, back right, half an inch. Oh, sorry, back quarter. Right an eighth. Yeah. Go back 16th then. Half as far again. This
would take forever.
Oh! Damn.
Hello? Hello?
Good evening, and welcome to the Hotel Hilbert.
Thank you. Look, I know you're full.
Absolutely, but we always have plenty of room here.
Great. I saw the sign, but I thought I'd...
Thought you'd just come to check to see if we still have any rooms.
Yes, that was the idea.
We have limitless numbers of rooms, so there's no need to concern yourself.
So, although it says hotel full, there are vacancies.
Oh, yes, indeed. Now, could I have your full name, please?
Knight. Fiona Knight.
Fiona Knight.
Shouldn't you take that hotel full sign down?
Why should I do that? We most certainly are full.
But you're giving me a room, aren't you? So, if you're full, how can you?
Quite easily. It is an infinite hotel, Miss Knight.
Which basically means that however full we are, we can always accommodate another guest.
All we have to do is move everybody up a room, leaving room 1 free for entry.
You move everyone?
Precisely.
Oh, no, look, I really don't want to put anyone out.
Oh, you're not putting anyone out, Miss Knight. That is how it works here. There you are. Come along, Miss Knight.
Good evening, ladies and gentlemen. We're very pleased to welcome a new guest to Hotel Hilbert. Now, in accordance with hotel procedure, would you please move up to the next room in sequence?
I thank you. This is room 1. Your key card. Now, all we have to do is to show it to the computer lock, and as if by magic... good evening, Mr. Schroeder.
Good evening, Penny.
Miss Fiona Knight. Mr. Schroeder was the guest in this room. He's now in room 2.
So people literally do move rooms?
Oh, yes. And when our next guest arrives, you too will move up a room.
Why would I want to do that?
So that we can fit every new guest in.
Well, can't you just put them in the room at the end?
Ah, but all our rooms are full.
So, every time a new guest arrives and we all have to move up a room, what happens to the person in the last room? The highest number room?
There is no highest number room.
No highest number room? Oh, but surely. I mean, what happens when you get to the end of the corridor?
There is no end to the corridor in an infinite hotel. Everyone loves this room, as well as the next one, of course. I think it's the view. You'll be able to see forever when things get a bit clearer.
Diamond of a life to unfold all the precious things love has in store. We have all the time love in the world. If that's all we have, nothing more. Every step of the way will find us with the care of the world far behind us. We have all the time in the world just for love.
Uh-huh. Dial 1 for reception. So where's the 1? How real is real. Very helpful. Beats Gideon's Bibles, I suppose. What? Oh. What's this? Life and Opinions of Tristram Shandy. I am this month 1 whole year older than I was this time 12 months, and having got no further than to my first day's life, 'tis demonstrative that I have 364 days more life to write just now
than when I first set out. So that, instead of advancing in my work, I am just thrown so many volumes back.
Every day of my life was to be as busy a day as this, and the transactions of it take up so much description.
At this rate, I should just live 364 times faster than I should write. It must follow that the more I write, the more I shall have to write. And consequently, the more you read, the more you will have to read. I ask you, will this be good for your eyes?
Not if this goes on, it won't. What is going on?
Dad! How are you? Settling in, all right?
Well, not so sure that I am, actually. Do you know how to get those phones to work?
Having a little trouble getting through to reception.
Well, yes. I mean, how do I dial 1 for reception when there is no 1 on my phone?
Well, you could try dialing 0.9 recurring, but that would take forever. It's usually quicker to go down in person. This way.
Why is the porter zigzagging down the corridor?
Oh, well, he has to make his deliveries that way. If he started going down one side of the corridor, he'd never get back to do the other.
Suppose he could just go on forever.
And finally, here is your key card, which operates your computer entry box. We hope you will enjoy your stay at the Hotel Albert. I'm sure you will find room 1 to your satisfaction. Miss Knight, I'm delighted to be able to inform you that since we have a new guest at the Hotel Albert, the rule of moving up a room now applies to you.
Oh, infinity plus 1, so now I'm in room 2.
Excellent. I'm delighted to see you're getting into the swing of things.
Well, I suppose you better give me the card to room 2, then.
No need for that. It's been automatically reprogrammed, and the porter will convey your luggage.
And what's he going to do? Drop my bag down the nearest black hole?
I beg your pardon?
Well, I take it the baggage handling arrangements here are infinite as well.
Our founder, the mathematician David Hilbert, 1862 to 1943, was always most particular about standards. Your luggage will be well cared for, Miss Knight. Any other questions?
Yes, there were, but they can wait. Which way is the bar?
Oh, we have a series of bars. We have the iterative bar down there, the convergent bar over there, and the recurrent bar down those stairs. And now, ladies and gentlemen, I'd like to welcome a new guest to the Hotel Albert. And now, please stand by in readiness to move in accordance with the rule infinity plus 1. Room number 1 to room number 2, room number 2 to room number 3, room number 3 to room number 4, room number 4 to room number 5, room 1 to room 6, room 1 to room 2, room 3 to room 4, 5, 6, 8.
Oh, wow, wicked. Hey, Sand Reckoner, what's Archimedes giving you for homework then? Hey, I'll tell you what, after 4,000 years of that counting, it could just be your turn to buy a round.
Good evening, Miss Knight. Settling in, I hope. Can I get you something?
Yes, an ordinary gin and tonic, please.
Gin and tonic.
By the way, do you think you could get someone to look at the bedside lamp in my room? Well, room 1, actually. It's just that it keeps switching itself off.
Well, of course it does.
Sorry?
It's a Thomson lamp.
Ah.
Same again, Mr. Bernstein?
Same again, plus 1.
That's what I like to hear. One of our regulars.
You got a problem, babe?
No, it's just the lamp in my room. My ex-room.
The Thomson lamp.
Yes.
In my experience, one thing you won't need in this hotel is someone to fix a Thomson lamp.
It'll come clear soon enough. All you have to do is remember that when it's switched on, it will switch itself on and off all by itself. And the interval each time will be exactly half that of the previous interval. 1 minute, then half a minute, a quarter minute, and so on.
But is it on or off after 2 minutes? You won't find anyone to sort that out either.
It's a paradox.
Penny, can I have you back in reception, please? We're suddenly really rather busy.
Everyone all right? I'll see you later.
Never gets turned away from the hotel helmet.
Oh, she's an awful racket out there.
Oh, that would be another infinite number of people arriving, I expect.
Happens all the time.
But how will they take in an infinite number of new guests?
If they're patient, they'll all get a room. They always do.
Still an awful lot of people to check in.
Yes, but they'll manage it. It isn't a problem.
Oh, so we're going to be shunting rooms all night.
Not to worry. If you've stayed at this hotel as often as I have, you'll understand the way Ted works. What he'll do is move us double the number of our present room and leave the others free for the new arrivals.
So we'll all be in even-numbered rooms now.
Leaving an infinite number of odd ones for the newcomers. Infinity plus infinity is infinity.
Infinity plus infinity is infinity. Who is that?
Oh, that's old Shandy.
Would that be Tristram Shandy?
The very same.
I never even saw room 2.
Don't worry, you'll see plenty more. Come and see mine if you want. Room 32. I'll leave the light on there.
How would you go about losing someone in an infinite hotel? Morning. Hello?
Don't interrupt me. I'm busy.
What are you doing?
I'm counting sand.
What, all of it?
I am counting all the world's sand.
Are you by any chance counting all the grains of sand in the world because there are an infinite amount of them?
Not at all. You're confusing large numbers with infinity.
Well, what's the difference?
There is a very large number of grains of sand in the world, but there is not an infinite amount.
So, in theory, you could come to the end of your task then?
Indeed. When is a different matter, though.
Yes, I see.
My task was begun 4,000 years ago. No, look what you've made me do. They'll have to start all over
Ah, fancy a game, Miss Knight?
Oh, what is it?
Zeno's game. Nothing too physical, more sort of mind game. Come along, number 2.
What sort of archery without the bows?
Sort of. It's a paradox of Zeno. Quickly, number 1.
Now, what's the paradox this time?
That if you fly an arrow 50 yards towards its target, it has to travel through 25 yards before that first.
And?
And 12.5 yards before that, and well done, number 3. 6 1/4 before that, and so on and so on.
Making it an infinite number of steps before the arrow reaches its target.
Precisely. And because it is an infinite number of steps before the arrow reaches its target, Zeno proposes that motion is impossible. Quicker, number 1.
Oh, no, come on. That's mad. Look, of course motion's possible. They're all moving around.
Ah, yes, they are. But they continue to rack their brains over it, don't they? Such is thought in an infinite life. Ah, Miss Knight, before I forget.
Don't tell me, Mr. Bevan, I've got to move rooms again.
That's right. You've got a new room.
Well, I thought you'd never ask.
Closures in our hotel chain, I'm afraid.
Oh, not serious, I hope.
Not a problem. But an infinite number of our hotels has closed this time.
An infinite number of infinite hotels?
Yes, we've had to take in an infinite number of infinite numbers of guests.
Ah, so now let me see. That's infinity times infinity. Well, that must have been a bit of a blow to the system.
It wasn't a problem. Everyone had to double up. Double the corridor. So if you're on corridor 2, you're corridor 4, 4, 8, 8, 16, and so on and so forth.
But I thought it was the number of rooms which was endless.
And the number of corridors.
So there's an infinite number of corridors as well?
As I said, we had no problem in accommodating a new infinite number of infinite numbers of guests. Your card has been reprogrammed to 4 on 2.
Right, well, it's after 4 on 2 then.
The lift is that way, Miss Knight.
Thank you. I can't wait to see those buttons. Another one of your games, Mr. Bevan. Very interesting.
Only because of your sixth sense, Miss Knight.
My sixth sense?
Your sixth sense. That's what makes the hotel interesting.
Well, I don't think I have a sixth sense.
Oh, but you do. It's your imagination. The most infinite concept ever. You're going up?
Actually, no. I don't think so.
Well, nothing to be worried about, Miss Knight. You can get to every corridor in the hotel. You just press 1 for every floor.
Yes, but you could be pressing those buttons for a very long time, couldn't you? The guest wanted to go to the top floor.
And what top floor is that, Miss Knight?
The last one. The one where the lift crashes through the ceiling.
But there is no end to the elevator shaft. Either way, this is an infinite lift.
I know, and that's exactly what disturbs me.
Is everything all right, Miss Knight?
I'll just take the stairs.
They can be awfully tiring.
Yes, but if that lift breaks down, it doesn't just drop, does it? It drops forever. We'd never get to the ground floor. We'd never stop. We'd probably just go through it and never stop.
There's no need to panic.
In fact, if you think about it, we'd probably go straight through to the Earth's core. So no, thank you. I'd rather walk.
Miss Knight, Fiona! If you don't try to understand how this hotel affects you as a person, you will be merely a spectator and not a participant in an infinite world.
Oh, I'm sorry.
Good evening, my dear lady. My name is Tristram, for which I apologize.
Apologise?
It is a melancholic dissyllable, connected, I believe, with post-coital distress in animals. And you, dear lady, are...
I'm Fiona Knight. I don't want to push you out or anything, but I think this is supposed to be my room now.
Oh, I must have been so engrossed in my writing that I failed to hear the manager give out the new rule. What was it, by the way?
Everybody double up the corridor.
Oh, please excuse me, Miss Knight.
You're a writer. I've seen your work.
My life and opinions. Yes, I've been writing these all year.
And if I've got it right, you're 364 days behind.
Indeed. I have so far only completed the first day of my life.
Yes, and you'll never catch up. Your writing will always be behind by a year or more.
I shall be at it for all eternity. But this way, you cannot single out a day when it is not possible for my records to be completed. It's just that as time goes by, I get further and further behind.
And your writing process is infinite too.
Of course. Perhaps that's why I'm here, to stay. Good day, Miss Knight.
Good evening, Miss Knight. Would you care to peruse the menu?
I take it this is infinite too?
But of course. You can have any combination of your choice.
Including infinite combinations?
Naturally. I mean, but of course.
So can we assume that this meal could take a very long time to come?
Very good, Miss Knight.
I'll give it some thought.
I thank you.
How delightful to renew our acquaintance, Miss Knight.
I've got something for you. You left it in the room.
Ha! Corporal Trim. Yes, I was wondering where he'd got to.
Mr. Shandy, Tristram.
Dear lady.
All this infinity business.
Infinity? Oh, yes.
Well, it's all very interesting in an intriguing sort of way, but it occurs to me that when it comes down to it, it seems to me that, well, all infinities are all the same.
Infinities, they are not all the same.
Yes, but look, whether you turn up here alone, or in an infinite party of guests, or even infinite parties of infinite other guests, you all end up in the same set of rooms. Infinity plus 1 equals infinity. Infinity plus infinity equals infinity. Infinity times infinity equals infinity. It's all much the same thing.
Not so. There are infinities which are even beyond the Hotel Hilbert. Take, for instance, the menu.
Yes, this is infinite too.
And that's one infinity. But all the possible choices from the menu...
Including infinite combinations.
All combinations, including infinite combinations, is a bigger infinity. Every guest in this hotel could eat something different, and there would still be choices that nobody had picked.
So, all infinities are not the same.
Indeed, no. If every one of the infinite guests took... Oh, I don't know. Let me see.
A star.
Ah, but we do not know that the stars are infinite in their number.
Yes, but if they were, then a constellation is just a choice from the infinite number of stars. So, including infinite choices, well then, there'd be a bigger infinity of possible constellations. Wow.
What really matters
is that you accept the challenge of the idea.
It's your imagination, Miss Knight, the most infinite concept ever.
Don't be frightened, no need to panic.
If you don't try to understand how the hotel affects you as a person, you'll be merely a spectator.
Instead of a participant in an infinite world.
Be brave enough to swim with the current.
Honest enough to explore a new idea.
Through unworldly track.
Can I ask a question?
What's that, Miss Knight?
Does anybody have any idea how all this is supposed to end?
Has anyone seen my telescope?
Look, if we get rid of that...
And you drop the O in Fiona.
What you're left with is...
Fiona Knight becomes finite.
I think I ought to be going now.
No, look, Miss Knight. If you leave now, you'll leave us with an empty space which you'll never be able to fill.
And your empty place would permeate through all the imponderable space of the Hilbert Hotel.
Your move, Miss Knight.
I've got a suggestion. Why don't you stick an N in front of the finite?
Oh, very good. Infinite. Oh, very, very good. Marvellous. Oh, thank you.
There you are then. All's well. All will be well. This could take forever.
Wasn't used to the university environment, so that was a bit scary, but in fact I've been made to feel very welcome. As well as further education, it's also opened a lot more doors for me. It's opened up a whole new world. You get to meet so many different people from other walks of life.
Recent political history here on BBC Learning Zone now as the OU takes a look back to the 1997 election.
Conservative Party, 19,137. Twig, Stephen, Labour Party, 20,507.
On the 1st of May 1997, the Labour Party swept to victory, gaining a majority of 179 seats. The scale of the victory had been unexpected and raised popular anticipation for real change.
I sometimes think New Labour went to the beach to have a paddle in the water and were hit by a tidal wave. And it was really on a huge scale. And the scale of that indicates, in my opinion, the scale of the rejection. But it wasn't just a rejection of the previous cabinet. It was a rejection of many of the ideas that would be now described as part of the legacy.
I should say to you that I have just
community. It also has to take on some of these aspects of looking like the home and the house, that it's long-lasting, that it's enduring, that these roots are deep roots. And to do that, it has to present itself as old in some way.
And so even the sense of being old is in fact itself constructed.
Absolutely, yeah.
Margaret, thanks very much indeed. The next program is about changing lives. It's about the different stages in life and how we change as we go through life.
Number 2, 5 and 1, 51, 6 and 8, 68.
Gordon Grant could win it, and now the points gap grows.
Jenny Stout is also going well, so the favoured runners more or less level at the moment.
So do look out for that. It's wearing a blue collar with a yellow disc. That's Taro, the tabby cat. Contact Kim Weston and I'm sure it would make her day. Hold on to your stomachs now as BBC Learning Zone finds out what puts a thrill into a roller coaster ride.
It's 6:30 one morning in late summer at Alton Towers Amusement Park. Phil is part of the regular maintenance crew checking out the Nemesis ride for safety. He'll look at every one of the 716 metres of track and every one of the 7,400 bolts. The suspension is checked on both the 32-seater trains, which each carry up to 1,400 passengers an hour. Only when the operations crew is satisfied do the cars make their way from the maintenance bay onto the track for the first passengerless test runs of the day. And only when the crew is completely confident is the ride handed over to the presentation staff who will run it. An hour later, the first paying customers of the day follow the crew around the track, and you begin to see why the Alton Towers staff took so much care.
I'm just shaking. It's just an experience. You're here, there, and everywhere. I looked once, and that was bad enough. All I was going to see was feet and arms flying.
I was a bit nervous to start with, but since I got on, I was okay. But no, it seemed to be all over very quickly. That's the only thing.
Thank you. I'm still shaking.
It's fashionable to be frightened, and the designers of rides know it. Successful amusement rides are big business. A market-leading ride might cost $10 million to design and build. In this program, we're going to try to understand why they're built that way. A combination of engineering, psychology, and physiology. Design starts 2 to 3 years before the rides are built to allow for independent cross-checks and for arguments between the different design responsibilities. But when Nemesis was installed, it was chosen to have this effect on the passengers, this effect on the supports, and to miss the cosmetic decoration, the theming, by just this amount. Even the fact that the initial ascent is a long, slow haul is part of the game. It's more likely to build anticipation than an elevator. Long before the first passengers joined a lengthy queue, the designers knew exactly how fast they would be travelling subsequently and what forces they would feel at every stage of the following terrifying, delicious, scary, and horrific 90-odd seconds. The trouble with understanding a ride like this one is that it's too complex. The track's all over the place, let alone the forces and accelerations you have to understand. Even stripped of everything but the essentials, it's hard to work out what's going on. What you need is a mathematical model of the behavior of the ride. And here, you can learn from the designers. They ignore the twists over the geographical map and model the acceleration you experience meter by meter along the track. The coordinates are those of the riders, up, wherever that is, temporarily, sideways and forwards. So you end up with a profile of the track. And now you can explore how Nemesis affects its riders. We mounted a camera on the front for a grandstand view of how they looked. And then we added the track profile. As we're carrying our coordinates around with us, up is the top of the screen. That's where the sky is, for the moment. You'll see this sequence again later, when we add in the forces experienced by the riders. But to understand those forces, you need to take a look at some older, simpler amusement rides. We took an OU academic, a psychologist, and an engineer on a tour of the amusement parks to find out why we're scared and what the designers are worried about.
This first ride, the rotor, is a bit like putting people in a spin dryer. Basically, you're just making them whiz round and round and round, and it seems so simple to me. I can't imagine what's thrilling about it.
Well, I think with most fairground rides, what thrills is the fact it gives you an experience which is so very different from anything you'd normally have in everyday life. And in this case, I think what usually gets people is the point where they drop the floor away. You're going so fast that centrifugal force throws you against the wall. They lower the floor, your feet are left in mid-air, and the world isn't supposed to be like that, so of course everyone screams.
What sort of accelerations are involved in this one then, Gary?
Well, this particular type of ride, the acceleration can be as high as 6G, which is rather higher than you'd find on a roller coaster. This particular one seems to be about 4G. This is the centrifugal force acceleration into the wall.
It's natural to think that the riders are being forced back against the wall, but the mathematicians prefer to model what the wall is doing to the rider, producing an equal and opposite reaction. The wall produces a force of 4 times body weight, an acceleration of 4G. The rider's weight pulls them down. Friction pulls them up. We can combine friction and weight in a single acceleration. When you combine that with the one from the wall, it comes down to just one acceleration in this direction. Normally, you'd experience that only if you were lying backwards, which is just what a rotor rider feels.
The next ride we're going to look at is the Yankee Flyer. It introduces the next bit of complication, because instead of whirling people around this way, like the rotor, with a constant outward acceleration, it whirls people around this way, which means we have 2 accelerations to worry about. We have the outward acceleration, and we also have the acceleration due to gravity associated with weight.
The essential design feature with the Yankee Flyer is to get the rotational speed correct. You choose that so that the acceleration produced radially is just less than that due to gravity.
I imagine that's quite important, because what about at the top if you...
Yes, that's the point. At the top you're nearly weightless, but you don't want to be totally weightless. We don't want the passenger to leave contact with the seat. We don't want him bouncing when he lands.
So again, we have a constant acceleration, but one that's changing in direction. As before, we look at what the ride is doing to the passenger. As it rotates, it adds this to what the rider already experiences. It affects the rider's weight by a varying amount. At the top, it acts against it. At the bottom, it reinforces it. In between, its vertical contribution varies. So the upward acceleration on the rider, felt as weight, varies between 0 and 2g.
Peter, am I right in thinking that with the Yankee Flyer the most thrilling thing is the near weightlessness at the top? Yes, I'm sure that has to be one of the high points, you might say. It's an unusual experience for people to feel that they're just about to leave their seats, and of course the opposite at the bottom where you suddenly feel heavier, like a roller coaster. But there is more to it than that. As you were explaining, as it revolves, the outward acceleration, it's always along a radius, and that means that, for example, over at our side here, when it's at about 9 o'clock, you've got the acceleration that way, plus gravity still downwards, and the resultant at about 45 degrees. Now, normally I'd only experience that kind of feeling if I was leaning over like this, but here the passenger knows he's still sitting perfectly upright, and experiencing this revolving force as if he was turning cartwheels. And the result is that, again, there's this mismatch between what the eyes and everything tell you, and the gravity sensor in your head is saying that you're turning over, and you probably feel rather sick as you get off.
Now that we've seen the effects of accelerations when they're relatively constrained, it's time to put them together and look at a roller coaster, albeit one simpler than Nemesis and without the theming.
Right, well, this is the typical starting point for a roller coaster, where the train has to be got out of a low-level station and be given some potential energy to convert into subsequent velocity. This is the powered section of the circuit, where the roller chain will carry it up to the top, and just this side of the roller chain is a ratchet device, which is actually an anti-rollback safety device, in case the train should decide to roll back towards the station.
Of course, from the psychological point of view, for the rider, who's not worried about building up potential energy, what all this does is building up the anxiety level as they gradually gain height, and the clicking of the ratchet all the time all adds to the tension.
The designer now wants to use this potential energy in as thrilling a way as possible, and that comes down to what can be contrived with the accelerations. So how do they vary around this ride?
Well, after the lift, we've now got our potential energy that we can convert into velocity. And here we come into our first dip, where we've got a significant force into the seat of the car.
The track's still horizontal from side to side, of course, at that point. There's no camber, so the sensations that people have is merely that they're upright, but they're being pressed into their seat a bit harder.
That's right, yes. And of course, when we get up here, we've started to introduce a bit of camber to get round the first bend, but the velocity's fairly low and it's a fairly slight camber. The track then comes round and through another dip, but by the time we get round here, we've got about our third dip. And at this point, we've got a very tight vertical radius, just over a short distance. And at that point, there's a high force into the car. Then as we go up and round again, you can see now that we've got a much more cambered track, if you can compare with the track above it. We have more velocity there, and the camber is required to stop the passengers being thrown from side to side against the shoulder restraints, to keep the force directed into the seat.
And that's at right angles to the track.
That's at right angles to the track.
So in a sense, of course, the forces are always downwards, which is what people experience normally in everyday life. It's just that they feel that they're weighing a little more.
That's the aim, yes.
A nice feature about this bit is that as you come out of that bend and down the slope, you're rushing towards these two pillars and the other piece of track above the top. And of course there's bags of clearance, but approaching it at speed, it's very hard to make that assessment. And you find that even in very young babies, if something rushes towards their faces, they'll try to blink and flinch. And typically, of course, with roller coaster riders, you do see them all duck at this point of the ride.
Yes, well, the other interesting feature to me is the change from a right-handed curve into a left-handed curve as it crosses the centre of the ride here. And what this is actually meaning is that we have to have a rapid change in camber angle, and the track has to adjust and twist round so that we can balance the forces again into the seat. Well, we're getting towards the end of the ride now, and we're spiralling down with increasing velocity into the tightest part of the circuit. The total forces are at a maximum round here, and by the time we get round here, we've got to have a very steep camber angle. So at this point, we're probably looking at something in excess of 45 degrees.
And yet, of course, although it's cambered like that, the forces are still perpendicular to the track. So the riders still feel this tremendous force down through the seat, the greatest yet, so it's quite an experience for them. And interestingly, of course, although their balance organs are all telling them that down is in that direction, their eyes are telling them that the horizontal is in that direction. And it's that kind of mismatch which generally produces things like travel sickness. And I'm sure that if people were on this ride for long enough, they would get quite sick.
This ride at Wicksteed Park is child's play compared with Nemesis, and yet even this one could make you sick. What might Nemesis do?
It was exhilarating to begin with, but I felt really sick towards the end of it. The twists and turns were terrible, particularly the final one. When you thought it was over and then suddenly there was this terrible twist and down at the end. That made me feel really sick.
It was extremely fast. I feel quite sick on the ride. It is all the twists and turns that actually make you feel very, very sick. My legs at the moment are very shaky still. It was a good ride though. It was worth going on.
Gary, now we're far enough away we can hear ourselves think a bit. Let's discuss the design of the Nemesis. I mean, the first thing that strikes you is that people are being whirled in every possible direction. From the design point of view, what does that involve?
Well, the modern generation of roller coaster has introduced the possibility of turning the passengers upside down. The designers realised that they'll accept this. And this actually means that we can now introduce vertical loops, helices, and various other shapes. And it generates, of course, a very complicated looking shape geometrically, and something like a sort of Gordian knot that has to be unravelled so that we can find out the accelerations that are going to affect the passengers.
So let's start unravelling the Gordian knot. What do people expect from a ride like Nemesis?
Looking forward to it?
Yes.
What do you expect it to feel like?
Terrible.
Scared stupid? But it's still worth doing. Yeah. It's the scariness that makes it good. Yeah. But you're going to go nevertheless.
I'm going all the same, yeah.
How do you expect to feel?
Terrible.
It's your first time here?
It is.
Looking forward to it?
I'm not sure yet.
What do you expect it to feel like?
Painful. I think it's going to scare the living daylights out of me, actually.
But you enjoy being scared?
Yeah.
How do you expect it to feel other than terrible? What will it? You've been on roller coasters before?
Frightening. It's very fast.
Everyone expects to be scared, and some people think it's the speed that does it. It's not. This display is speed along the track. It never rises above the maximum of 80 kilometers per hour, less than most people drove to the park at. So if it isn't speed, what is it?
So which bits have been designed to be the most thrilling, do you think?
Well, the positions where the accelerations are highest, and those typically, of course, are the lowest points on the track, where you've got the highest kinetic energy, highest velocity.
So how does acceleration vary as you ride Nemesis? This display is showing the acceleration in the up direction, what the rider feels through their seat. It's more variable than speed and changes between a maximum of 4G and 0, which is weightlessness. But that's much less than the rotor. You could feel 6G there and still not be scared. This third display, here it's negative, is part of the reason. It's how fast the acceleration changes, something roller coaster engineers call jerk. On the rotor, the jerk display would remain firmly set at 0. On Nemesis, it's adding to the thrill. There was jerk changing acceleration on the Yankee Flyer too, but there it was constant. On Nemesis, the jerk changes. The engineers even have a word for that change. It's jounce. the rate at which the jerk is changing. It's not a large change, but notice it isn't constant. Speed, acceleration, jerk, and jounce. To the designer, it's the jerk that counts.
What about the way the acceleration is changing? Does that have something to do with it?
Yes, that is the jerk, of course, and we want the jerk to be contained within reasonable levels. This has implications for the structures. And the jerk, of course, changes where the transitions in the tracks from one radius to another occur.
And what about on the corkscrewing bits?
On the corkscrewing bits, of course, you've got a continuously changing acceleration, and the camber can normally be chosen so that the acceleration changes smoothly. In that situation, the jerk is quite low.
So the key to the design is the choice of camber, then?
Absolutely, yes. Get the camber right and you avoid the side forces and you keep the jerks within reasonable values. The sideways accelerations we want to limit. We don't want the passengers thrown too much from side to side, and nor do we want those sideways forces on the structures. It introduces stresses that are undesirable in the long term.
Gary's reminded us that the accelerations on the passengers aren't everything. The structure has to be safe as well, and so do the riders, which is why they have to measure up too.
So, how was it then?
I don't know, I couldn't get on the machine.
Well, that's a bit mean.
Yeah, my chest was too big, I couldn't get the guard to lock.
Bad luck.
So my wife's on there.
So we'll have to ask her what it was like.
Yeah. Unfortunately, I didn't fit on.
But there's still hope for those who don't fit onto Nemesis.
Perhaps this kind of thing is where the future lies. Take a platform and mount it on 3 hydraulic jacks. Control the hydraulic jacks with a programmable controller, into which you've fed all the forces and resulting accelerations and changes of acceleration that you would expect from a ride that you've already filmed. Put a passenger cabin on top of your platform and project a film of the ride in front of the passengers and subject them to all the rises and falls and tilts and jerks that you would expect during the ride, and lo and behold, you've got the fairground simulator.
It wasn't as convincing as I hoped it would be, but it was enjoyable. It was very jerky, but definitely not as good as a real thing.
Once you got going, you really did feel like you were on the roller coaster.
There was a feeling of acceleration, but nothing like what I would have expected from the size of the ramp that it was in, giving the impression it was going down. I think if you'd been on the real ride that's been used for that, it would have been totally different.
A simulator can operate virtually anywhere, at any time of the day or night. Once you're inside the box, the experience is always the same.
When you're coming up to go over an hill, it's like you're going up to go over this hill and you're thinking, now, I wonder what's going to happen when it goes over the other side. It shoots you forward like that and you sort of get a grip. It's quite good, really.
It made it feel really real.
It might not be quite as real as Nemesis, but it models the jerk and the jounce. Whether it replaces all the fun of the fair is another question.
If you would like to know more about the Learning Zone, you can telephone the BBC Education Information Line on 0181 746 1111, Or you
change in the question of aging, isn't there? Because the demographic shifts in British society are now very dramatic. Aren't they going to rejig our whole notion of what the different ages correspond to? What are the life tasks of youth and middle years and age and old age? I mean, there are new categories coming up even at the end of what we used to think of as the end of life.
Yeah. I mean, Laslett emphasises this point at the end of the programme, and certainly the changes do seem quite stunning if one compares, say, from the beginning of the century, when life expectation is around 50, to the present time, when expectation is around about 75. We're talking here about a 50% increase in what the length of life that one can expect to live.
Yeah.
And, of course, the much greater proportion of people over 60 who are in our population. And as Laslett points out, this is changing our whole conception of what life is about.
Yeah.
That maybe 50% of our life may be spent post-retirement if we, say, take early retirement in the 50s, as many people do.
Very dramatic. Yeah. Dick Stevens, thank you very much indeed. Next time we're going to look at a program which is called Regions Apart. It considers the relationship between different regions in the global economy and underlines the course theme of the relationship between the local and the global.
Understanding War and the Causes of War on BBC Learning Zone now, as the Open University investigates the mathematics of conflict.
In the midst of the First World War, two individuals applied ideas from mathematics in their attempt to assure that this could never happen again. Frederick William Lanchester used a mathematical model in his argument for a massive increase in the production of a new fighting machine. And in the same year, Lewis Fry Richardson used mathematics in his analysis of the disastrous consequences of an uncontrolled arms race. As a young man, Lewis Fry Richardson had worked for the Met Office. He was to be the first person to develop detailed mathematical models of weather systems. However, in 1916, he found himself on the front line in France. His enthusiasm for mathematical modelling continued in his study of weather. But he had already begun to apply his skills to a more immediate problem. While in the trenches, he wrote a key paper, The Mathematical Psychology of War. Richardson saw the opportunity of modelling one of the most complex forms of human behaviour. His paper contained a detailed mathematical analysis of an arms race.
Mankind is surely more complicated than lifeless matter. It is therefore not reasonable to expect that we should understand mankind by using techniques simpler than those required of physics. Mathematical expressions are in general use in various parts of sociology. For example, in economics. and in all cases where statistics of large masses of mankind have to be described. It therefore seems reasonable to inquire whether mathematical language can also express the behavior of human beings in another case in which they also act in large groups, namely in war.
Richardson was a Quaker, and this determined his attitude towards war. He was a pacifist and he wouldn't fight as such. Nevertheless, when the First World War came along, he volunteered for the Friends Ambulance Unit, which meant that he was at the front for quite a while. He saw the war really at the sharp end, just as much as any infantryman did. He was horrified, as were many young men at the time. But whereas many of the poets of that generation, justly famed, wrote their poetry, Richardson instead wrote equations.
Richardson's strong belief in the power of mathematics to uncover the fundamental nature of a problem was matched only by his deeply held moral convictions.
I have a prejudice that the moral evil in war outweighs the moral good, although the latter is conspicuous. This prejudice is derived from the Quakers who brought me up. I am not ashamed of it. Indeed, it is one of the two principal motives for writing this book. The other principal motive is my prejudice that scientific method is more trustworthy than rhetoric. I am not ashamed of that either.
Richardson felt his new analytic approach might reveal the potentially devastating consequences of an uncontrolled arms race. If two countries are in conflict, then Richardson believed that each country would adjust its rate of arms expenditure in response to the level of spending in the other country. This meant that the more red spends, the more blue's rate of spending increases, and vice versa. But Richardson knew that spending can't increase indefinitely. In the details of the equations he developed, he proposed that as well as psychological and sociological driving forces, there must also be braking effects. His paper contained over 30 different equations specifying the factors that would interact in determining the progress of an arms race. Maths was Richardson's preferred language of expression and analysis. It was also a powerful one.
Mathematics is a language which we use to describe reality. Its great power is that we can use it to work out long deductive chains, to see what is implied by what initial set of assumptions lead to what conclusions, which may not be self-evident, and this is what's important. This is where Richardson used it to great power. He showed that some apparently innocuous assumptions about what generates an arms race lead to all sorts of peculiar conclusions, some of which are just not obvious. If you want one simple rule about mathematics, or one simple claim for mathematics, it's in its ability to show what is true, which you hadn't thought was going to be true, and what is false, which you thought might be true.
To have to translate one's verbal statements into mathematical formulae compels one carefully to scrutinize the ideas therein expressed. The possession of formulae makes it much easier to deduce the consequences. In this way, absurd implications, which might have passed unnoticed in a verbal statement, are brought clearly into view and stimulate one to amend the formula.
After the war, Richardson continued to adapt his model in several papers, the most famous being The Statistics of Deadly Quarrels. In these works, he used his mathematical analysis to point to the possibility of an impending disaster if an arms race was left to run out of control. And in several papers, he predicted very accurately the arms race which led up to the Second World War. But using maths to model the future wasn't just the province of pacifists. Frederick William Lanchester used almost identical techniques to Richardson, but he used them to argue for a massive increase in the manufacture of a new fighting machine. Although Lanchester left school without any formal qualifications, in 1899 he won the RAC Gold Medal with his design for the first British four-wheel petrol-driven car. In 1922, he was elected a Fellow of the Royal Society. By his death in 1946, he'd applied for over 400 patents.
Well, certainly the range and the depth of his understanding were quite phenomenal. In just about everything he turned his hands and mind to, he tended to see the whole subject in the round. How it had to be made, how each detailed part had to be made to work most efficiently. He took a very similar line of approach when it came to the aeroplane, producing the first consistent aerodynamic theory of the aeroplane before the world knew that the powered aeroplane had actually flown. Basic wing theory is still named after him. Meanwhile, in his spare time, he was producing 2 volumes of poetry. He became an accomplished amateur leader singer, and then became interested in the problems of sound reproduction, setting up a small factory to make advanced loudspeaker systems. I could go on, but you get the drift.
Long before the war, Lanchester defined one of the first mathematical accounts of flight, including detailed predictions of the properties of wings.
He predicted, correctly, that the lifting force on an aeroplane's wing would increase as the square of the aeroplane's forward speed. He also predicted, again correctly, that the lifting force would increase in proportion to the angle of incidence of the wing to the approaching airstream. And remember, he predicted all this in 1907, 1 year before the Wright brothers gave their first public demonstration of powered flight.
Lanchester's interest in aircraft, in modelling them and predicting their properties, was no longer restricted to the physical characteristics of the wing. With the onset of war, he was now interested in their strategic role in battle.
Certain writers, basing their views too exclusively on the present war, have expressed the opinion that the aeroplane, or more broadly aircraft, though of the greatest service as a new means of reconnaissance, will not have any material influence on the tactical employment of the older arms. In the opinion of this present author, this view is fallacious, and the present war cannot be taken as a criterion. It is unfortunately not yet possible to draw conclusions of a lasting nature from the actual usage of aircraft in the present war. The machines are numerically so weak that as an arm of the service, the aeronautical forces are a negligible factor. In order to effect anything decisive, an organization of an entirely new character is required. And in order that it shall be capable of fulfilling the duties assigned to it, it must be strong by virtue of numbers.
In 1916, while Richardson was writing in the trenches, pointing to the problems of arms races, Lanchester published Aircraft in Warfare. At the heart of the book was his argument suggesting an urgent need for Britain to produce a massive fleet of new aircraft, no longer just for reconnaissance, but now for fighting.
The maintenance of the present superiority of the British reconnaissance machine and the development of different types, and in brief, the building up and consolidation of the aeronautical arm, both as to quality and quantity, in order to ensure our capacity to hold our own with the other great powers, is a task of national importance and as such one of the first magnitude.
In the same way maths had helped him to uncover principles of flight, he felt mathematical analysis might uncover some key principles of battle. He felt that there were simple mathematical rules which could help strategists understand the outcomes of battles. His focus of interest was the way the nature of fighting had changed. This was to do with the new technologies of warfare, which increasingly allowed killing at a distance.
In primitive times, when weapon directly answered weapon, the act of defense was positive and direct. The blow of sword was parried by sword and shield. Under modern conditions, gun answers gun, artillery, artillery. But the defense of modern arms is indirect. Tersely, the enemy is prevented from killing you by your killing him first, and the fighting is essentially collective. With modern long-range weapons, firearms in brief, The concentration of superior numbers gives an immediate superiority to the active combatant ranks, and the numerically inferior force finds itself under heavier fire man for man than it is able to return.
Lanchester's model of conflict deals with only two opposing forces. In primitive times, he suggested that if two forces with roughly the same fighting ability met in battle, then both sides would lose fighters at about the same constant rate. So if the numbers starting battle on each side were not the same, then obviously the victor must be the one who started with the most combatants. But he knew that developments in modern warfare would change the mathematical relationship between the two sides. Now, attacks could be concentrated on enemy targets at a distance. Lanchester felt that this had changed fundamentally the relationship between the two fighting sides. There was a new relationship which, if understood mathematically, would reveal strategic lessons to radically change battle outcomes. Casualty rates are no longer simply constant. They're now proportional to the size of the opposing force. First, look at the effects on one side. Suppose blue faces a small red side. Once battle starts, the rate of loss for blue is proportional to the size of red and is relatively slow. However, if blue faces a much larger red force, then its rate of loss is much faster, because red is bigger. This model seems simple enough. However, it's complicated by the fact that both sides are fighting at the same time, and so both sides are affected by the ever-decreasing size of the opposition. In primitive warfare, the rate of loss on both sides was constant. But in modern warfare, there's a changing rate of loss. As each side gets smaller, its kill rate drops, and so its effect on the other side also gets smaller. His analysis also revealed a surprising feature of any conflict taking place in modern times, something he called the n-square law.
My discovery of the mathematical basis of concentration, military or naval, announced under the title the n-square law, will probably be regarded in years to come as the most important and enduring section of the work.
As two sides engage in combat, if we subtract the total numbers left on one side from the other side, we get a changing number of combatants left over. There seems to be no fixed relationship between the simple totals on each side. However, he found there was a fixed relationship between the square of the numbers on one side and the square of the numbers on the other. That is, at any point in battle, red times itself minus blue times itself will produce a new square number. And at any point in the battle, the square of one side minus the square of the other is constant. Lanchester knew that tactical implications would follow from his n-square analysis.
One of the great questions at the root of all strategy is concentration. But we must not focus too closely on the bare facts of concentration, but rather on the underlying principles, and seek a more solid foundation in the study of controlling factors.
Lanchester's new analysis suggested that the simplest and most effective strategy was to enter battle wherever possible with vastly superior numbers. If red can combine all its forces in one concentrated effort, then the impact will be devastating. Red doesn't just outnumber blue, its kill rate is also extremely high. So blue's casualty rate is very high. And as blue continues to get smaller, red suffers ever lower casualty rates. But what if the two sides are exactly the same size and have the same fighting force? According to Lanchester's model, there is a way for one side to gain an advantage over the other. Red starts off the same size as blue, but blue splits the red side and fights with one half, then the other. Blue will complete the battle the victor, an effect never found with constant casualty rates.
He went back in history to Nelson's battle plan for Trafalgar, showing that it was in precise agreement with his, Lanchester's, predictions of the outcome. Nelson intuitively had got it right.
Following his analysis, Lanchester felt that Britain had no choice but to develop a massive air force, since according to his work, the larger the force, the greater the advantage. His analysis also suggested that whatever the size of the force, enormous advantages would be gained by organising that force, leading him as early as 1916 to argue that the aircraft would need to fly in formation to gain the best fighting advantage.
The independent air fleet must base its strength on its numerical superiority, and it is precisely here that the need for homogeneity becomes manifest. Properly to assert the power of numbers, the whole fleet must come into action as nearly as possible as a single unit. And in brief, it must concentrate the whole powers of the combined fire on the numerically inferior enemy. And no fleet can accomplish this unless its components are able to move and act in concert.
Although Lanchester is considered today as one of the fathers of modern military operations analysis, it's unlikely that he was responsible for the fact that we did eventually develop such a force. Indeed, although the use of maths in military analysis is commonplace today, Lanchester was severely criticised, even ridiculed, for daring to think that mathematical modelling might be a powerful tool for battlefield analysis.
There are many who are inclined to cavil at any mathematical or semi-mathematical treatment of the present subject, on the grounds that with so many unknown factors, such as the morale or leadership of the men, the unaccounted merits or demerits of the weapons, or the still more unknown chances of war, it would be ridiculous to pretend to calculate anything. And the answer to this is simple. The direct numerical comparison of forces engaging in conflict is almost universal. Yet, such counting of forces is in itself a tacit acceptance of the applicability of mathematical principles. To accept without reserve mere counting of pieces as of value, and to deny the more extended application of mathematical theory is illogical and unintelligent.
The danger in the application of mathematics to the social sciences is that one oversimplifies, and one tends to think that one's real world consists of just the 2 or 3 variables that one started off with. They may consist of 100 variables, and these 100 variables may, in fact, make a big difference. So we always have to be very cautious and realize that our so-called theories are, in fact, models. They're simplifications of reality, which we can use to derive these very, very powerful conclusions, but always remembering that they are simplifications. The arms race theory was not just determined by cost and threat. There are other things too.
Richardson was never entirely happy with his work. He knew that his mathematical analysis, while brilliantly and effectively applied to meteorology, would have its limitations in the field of international relations.
There is a formal resemblance between psychology and meteorology. In both sciences, an enormous collection of observational data has been open to inspection for a long time. In both sciences, the attempt to find order among the miscellany of the observations has proceeded slowly, with many failures. In both sciences, there are too many circumstances occurring simultaneously for the comfort of the mathematician, who would like to make a neat, simple theory.
Richardson was a very subtle mathematician, and more to the point was a subtle applied mathematician. There is a gap, after all, between the mathematics and the reality it's meant to mirror. And Richardson knew full well the difficulties at times of bridging that gap. These are bad enough in physics and bad enough worse perhaps in meteorology. In the social sciences they're perhaps even greater. It doesn't mean that mathematics is not applicable, far from it. It means one always has to be self-aware of the approximations which exist between the mathematical language on the one hand and the reality on the other.
Mathematical expressions have their own special tendency to pervert thought. The definiteness may be spurious, existing in the equations, but not in the phenomena to be observed. And the brevity may be due to the omission of the more important things simply because they cannot be mathematized. Against this, we must be constantly on our guard. It will be impossible to avoid them altogether, and so they must be realized and admitted.
BBC Learning Zone brochure is now available. It gives full details of all BBC Learning Zone programmes until the end of March 1998.
Actual flows of investment about, for example, car models in the UK and Europe, because the market is Europe, then clearly that would be a matter for negotiation between, let's say, the northeast region and Tokyo. But Tokyo, I suspect, would actually have the last say. Now, in finance, again, this is arguable, but I would say that there's more of an interrelationship, but I think it's Tokyo and New York that actually have the running there. And London, it's convenient, but there again, so is Frankfurt.
It's not playing such a determining role.
I think it's a declining role.
John, thank you very much. Next time, we're going to shift from economic to political processes and look at the impact on regions of the development of the economic community in Europe.
At the same time tomorrow, the next programme in the series looks at what's behind modern attitudes to the environment. Now on BBC Learning Zone, the OU takes a look at three very different approaches to building by numbers.
In 16th century Italy, the architect Andrea Palladio specialized in designing villas for a wealthy and cultured elite. His buildings epitomized a long history of interest in the use of number and proportion in architecture. And he created an architectural style that's been copied worldwide.
Palladio was born Andrea della Gondola in Padua in 1508. He was the son of a stonemason, and his break really came when he moved to Vicenza, just north of Padua, when he was in his teens, and he became apprenticed to a workshop in that city. Now, Palladio we remember largely because of the opportunities he was then given to design buildings in the classical manner. He designed in Vicenza palaces for local noblemen, and particularly the basilica, which was the reclothing of an existing Gothic building, in a classical manner, using classical orders, Doric, Ionic, Corinthian, and so on. Palladio then went on to design churches in Venice, and those wonderful images one has going there as a tourist of looking across the lagoon at San Giorgio Maggiore, across the water. Quite a stunning image to see.
Palladio's interest in number set an agenda for architecture for centuries to come. His influence can be seen in many beautiful buildings. But was this beauty purely aesthetic, or is there a link to his use of mathematics?
Palladio talks about proportioning rooms, length to width to height, using harmonic numbers. He doesn't actually go on at length about this. It wasn't important for him to restate knowledge which was known to most Italians. Palladio uses exactly those principles when discussing in the Quattro Libri, his treatise on architecture, how a room should be designed, that the length and the width should be proportional to one to another, and that the height should be a natural resultant of, if you like, a marriage of these particular numbers. And they weren't just any old numbers, they were preferred numbers, whole numbers as well, rather than fractions.
Palladio preferred numbers that exhibited harmonious relationships within the dimensions of a room. These harmonies were equivalent to those found in the music of the period. It has been said that architecture is frozen music, and it was this idea that Palladio was trying to capture in his buildings. He believed that what was pleasing to the ear should be pleasing to the eye. Music in that period was based on the Greek harmonic system, where the steps between many notes were small whole number ratios, such as the octave being the ratio 2:1. Palladio used ratios such as 6:10, a musical sixth, one of the accepted harmonious intervals in Renaissance music.
The Villa Rotonda outside Vicenza is probably the most famous villa that Palladio designed. It's made up of a combination of square, circle, in terms of geometry. And it uses certain numbers, the use of 16, this perfect number, 6 and 10, combined in the distribution, in the shape of some of its rooms. Now, when Lord Burlington came to North Italy to see these buildings, he came back to London and designed at his own house, at Chiswick, a villa in the Palladian manner, and this is it, Chiswick House. This is one of the finest rooms in the Chiswick House. And the proportions of this building are actually taken from that of the Villa Rotonda.
How exactly does the observer become aware of these harmonious proportions?
What's important when appreciating a classical building is understanding that every part, every element within its design is intended to relate to the overall impression. So from the smallest detail of the ornament of a door frame to the door handle itself and the position of it up from the ground is all measurable. It's measurable firstly in relation to the human body, that which you can touch and hold. But obviously as the space moves away from you, there has to be a belief that those dimensions are continuing in its overall form. And if we move through to the room at the end here, which is cubic in quality, I think one can get another set of impressions of that in terms of its importance for the observer. Palladio sought perfection in everything that he did, as all good artists and architects of that period. And one remembers Leonardo da Vinci's image of the perfect man in circle and square, arms stretched out. That geometry and the figure come together wonderfully in a room like this, which is square in plan and therefore ceiling, but it has a cubic quality about it. These wonderful blue walls are punctuated by by windows, again using square geometry in terms of their shaping. And as one's eyes then drawn up to the very richly encrusted cornice, and then above these heavy brackets supporting the ceiling above, which show a figure floating on a cloud, one gets the sense of this microcosm, not only of the body itself and its perfection, but in terms of the architecture, the space which one then moves into.
Despite the evidence that Palladio used harmonic proportions in his designs, not everyone is entirely convinced of his total reliance on number and proportion.
There is a debate going on at the moment amongst architects and historians as to the relevance of numbers for Palladio. It's true that in his Quattro Libri he says very little about number. However, the designs of his buildings show plans, elevations and so on, with number covering them. And there is a frequency of certain numbers appearing, the 6, 10s, 16s, distributed throughout the plans and the sections. Now, the fact that he doesn't state the importance of certain numbers doesn't mean that they weren't important for him. And certainly the writings of his predecessors, Alberti for one, but also Vignola, Celio and others, makes it clear that number was of great importance for any architect, any artist concerned with the classical tradition.
There's also another aspect of space and the human body that helped to form Palladian design. 16th century art was dominated by the formalization of a system of viewing known as linear perspective, the seeing of the perfect whole from one single point in space.
This house is all about balance, about left matching right, and framed openings and clearly defined spaces. That works very well with the development of perspective as it happened from the 15th century in Italy, where space was measured and reduced to two dimensions in pictures, drawings and so on. It becomes more of a problem when one really moves through a space, though, and this is a dilemma that was confronted in the 20th century, where it was appreciated that whilst space may have perfection instilled within it, but that is an act of faith. It's something that the observer has to know about, be educated in, whereas really as we move through space, as light comes in from windows from different angles and so on, in fact, really, what concerns architects today is actually working with that, of being more dynamic, of creating an architecture which is more interesting, perhaps, than the static, still quality that was sought in the Renaissance period.
As music moved from classicism to romanticism and expressionism, architecture mirrored these changes in artistic thought. But mathematics was also changing, and by the beginning of the 20th century, architects were keen to express the changing relationship between the human body and the space in which we live. One architect, Le Corbusier, epitomizes this attempt to make new, more dynamic relationships between mathematics and architecture.
Le Corbusier was born Charles-Édouard Jeanneret in a provincial Swiss town known for making watches. But he came to Paris in 1917 and met a man, a painter, Amédée Ozenfant, who changed his life, and they created a modern art movement together, Purism. Le Corbusier began to use this professional name, Le Corbusier, and created a style of architecture which was very abstract, unrecognizable from anything that had gone before. Throughout his life, he flirted with mathematics. He flirted with mathematics because he was always looking for proof that what he was doing was right, was scientifically correct, was not something that just depended on an artistic authority. So, in one of the first books on Purism that he wrote, he talks about the golden section.
The golden section cuts a line in a ratio considered pleasing to the eye. It's possible to divide any line such that the ratio of the smaller to the larger part, A to B, is the same as the ratio of B to the whole line, A plus B. Only if these two ratios are equivalent is the line divided in the golden section.
At the same time, in the 1920s, he used in his architecture a rather different system, which was used by many architects at the time, for purifying proportional relationships. And it was an ad hoc system. It was called the place of the right angle. And you did it by taking a set square and finding relationships, lines that cross each other at right angles. And it's all very ad hoc. And he called this the tracé régulateur. And we can see examples of this applied to his buildings. Here's one, for example, that he did for the Maison La Roche. Now actually, this diagram, this elevation drawing, is a complete fraud, because we know perfectly well that he did this drawing long after he'd finished designing the building. It was a proof of that he'd designed a good facade, rather than an actual means of getting the proportions right.
But for Le Corbusier, it was not just a question of getting it right, or even of justifying it mathematically. He believed that aesthetic beauty had an underlying mathematical explanation.
Throughout his life, he'd been interested in proportions and solutions to the problem of dimensioning. It's not just a question of finding proportions, but of whole number dimensions which have a mathematical relationship which follows some rule. And what he found in the end was the classic system of the Fibonacci series.
The Fibonacci series is a sequence of numbers generated by a rule. The next number is always the sum of the previous two. Beginning 1 and 1, the next number is 2. The same rule then gives 2 plus 1, 3, then 5, 8, and so on. It's known that Le Corbusier used the Fibonacci series, but is it possible that Palladio drew on a similar idea back in the 16th century? Starting with 2 and 2, the Fibonacci rule generates 4. Then 6, 10, 16, and so on. And 6, 10, and 16 feature in Palladio's designs.
And much later on, when he came to publish his book on the modulo, he remembered these experiments, and he illustrated some of them, showing the diagrams and bringing out the mathematical points that underlay the structure. And this helped him find two scales, the red and the blue scale, which he had engraved onto a kind of tape measure, which he carried around in a little aluminium pot in his pocket at all times, which gave him all the dimensions you needed, up to just over 6 feet, for all the dimensioning of architecture. And it's said that when he came to design the Unité d'Habitation in Marseille, which was a project going on in this time, 47, 48, that he used this rule to the exclusion of any other dimensions. The drawings don't have dimensions on them. They only have references to the blue and red modular scale.
In his city, everything is used. The roofs are playgrounds. The sun penetrates everywhere. Each family in their flat gets privacy, a view, sun and shade.
Despite the different sort of buildings that Corbusier designed, some features mirror those built by Palladio. Could this reflect the use of a common attitude to space and proportion?
There's a kind of paradox here, that Le Corbusier had this attitude to number and proportion, which was a classical system. It's something that Palladio would have recognized as belonging to the great Western tradition. And yet his attitude to space would have been unrecognizable to these architects. When he came to describe the Villa Savoie, which is perhaps the most extreme of his villa designs in the purist period at the end of the 1920s, he used what he called the lesson of Arab architecture. This is what you learn from walking around Arab buildings. They can never be seen all in one go. They don't have facades. You have to move through them on foot, so it's a relative viewpoint. And relationships become apparent as your eye moves through a building. And if you think about it, that makes it almost impossible to think in designing terms, in any sense which is fixed to proportion and number, because there's a relativism there which makes that an irrelevant consideration. You never have, as it were, in that way of thinking, a pure elevation, a pure plan.
But Corbusier's interest in mathematics was not all-embracing. To him, it was primarily a means to an end.
Corbusier wasn't a mathematician himself, but I think if he'd had a maths teacher, they'd have been proud of him, because he asked the right questions. He was constantly curious about the relationships between things, and particularly relationships that appealed to his aesthetic sensibility. So he would make a judgment, that's a nice proportion, that's a nice size in something, and he would whip out his modular ruler to find out whether he was right. So that was the way that he treated mathematical relationships. Le Corbusier met Einstein once, after the war, and he describes in the modulo this meeting, which was obviously very important to him, and he described his embarrassment that he couldn't really explain the mathematical principles behind the modulo clearly enough to the great man. But he was very pleased that Einstein got the basic message absolutely right, because what Einstein said was, what you have here is something that makes the ugly difficult and the beautiful easy. And that's what Corbusier wanted.
Simplicity and beauty were characteristics that Einstein sought in nature. When he said, God does not play dice, he expressed his belief in a set of coherent, unifying principles which underlie the world. But that faith has been rocked more recently by developments in science and mathematics. Attempts to represent the modern world as an ordered and stable yet dynamic place no longer seem sufficient. Recently, many architects have become interested in how to represent not order, but disorder. Not stable patterns, but permanent instability.
You might say that mathematics and architecture began around the same time. However, the attitudes toward mathematics changed over the centuries, and probably the attitudes, that architects had toward their own work changed.
The Parc de la Villette in Paris is an urban development that attempts to reflect the changing nature of leisure in society. It was built on the site of a former slaughterhouse. The park's creator, Bernard Tschumi, began by looking at the geometrical proportioning system of the original site.
At first, I was fascinated by that notion and tried to develop our scheme for the new park on that old 19th century geometric set of relations. And very quickly I found that was constraints which had nothing to do with the type of constraints we were interested in at the end of the 20th century. So we decided to do something which was radically abstract.
The park was constructed from 3 interacting systems. First, a system of grid lines, spaced every 20 meters. The junctions of these grids then created a system of points, punctuated by red metal follies. Finally, the surfaces between the lines are used as recreational spaces. But what happens when these systems collide?
When the logic of the system of line would suddenly interact with the system of points, occasionally they did not coincide exactly in a perfect manner. So one had to give way. So you would have, for example, at the collision of one of the covered galleries with one of the follies, suddenly the system would have to make an exception, would sort of to break away. That sort of fragmentation, explosion, which was caused by the system of lines, intersecting, interpenetrating, colliding with a system of points, then an architectural moment happened. And here pieces of enamel steel would be removed, suddenly literally would have the interpenetration of one system into the other.
The 20th century has seen the realization of a new mathematical explanation of nature based on complexity and repetition, chaos theory. Could this new mathematics have influenced Schumi in the same way that maths had influenced Palladio and Le Corbusier?
It's not chaos theory in terms of the ultimate logic of chaos, because here we are talking about the fact you have conflicting logic. Each of those logic is absolutely ruthless in its precision. It's exactly trying to sort out everything in the most precise manner. But once you confront it to another logic or another system, you're not trying to find an overall holistic view that would sort of merge those two systems with one another. You accept the fact that they actually have discrepancies. And in the case of architecture, quite often, that place of the discrepancy, the place of the contradiction, is exactly the place where architecture starts to happen.
But how have perceptions of the human body and its relationship to space changed?
Palladio, and amusingly enough, Le Corbusier as a master of the modern movement, were both fascinated by a certain type of proportional system, which today has been quite replaced by a totally different perception, which is not necessarily based on the body, although the body is very important. The body is what experiences those spaces, but it's a cultural body. It's not only a physical body. It's a body that is part of an electronic culture, which receives its information as much from the wall of a building as from a television screen. And hence you're part of a culture, of a whole cultural world, and not in the park of nature. Today, you start to realize that you can, thanks to that very close correlation between architecture, computer, and mathematics, you can develop certain structural systems which have never been seen before.
To be fully tested. This is, after all, the essence of social science.
That programme was made in 1991. Now on BBC Learning Zone, the OU asks why the opinion polls failed to predict the outcome of the 1992 general election.
And our view is it's going to be a hung parliament. This election is too close to call, and the likeliest outcome is the Conservatives short by 25.
We've won tonight a magnificent victory. A victory that many people thought was beyond our grasp, but one which the Conservative Party always believed was there for the taking.
If Labour takes it well, it's doing well. If Labour doesn't take it, they'll be quite upset, I suspect.
And I, being the returning officer for the Basing constituency,
the 1992 general election saw a surprise win for the Conservative Party. Right up until the eve of the election, it was the Labour Party that was well ahead in the polls. Yet despite the eve of poll prediction of a hung parliament with no overall majority, the Conservatives gained enough seats to form a government. So why were the polls so wrong?
So if Basildon is typical, then wait for much, much, much less swing than the exit poll earlier was suggesting, but very, very early results here.
A new opinion poll published today in the Sunday Times shows that people have had a right gutful of opinion polls. Of those questions, 63% said, piss off, I've got a train to catch. 28% said hanging should be brought back, just wait there while I go and get a rope. And the other 9% said that they were small cubes of orange-coloured wood.
So, I'm from National Opinion Poll. We're doing a survey in the area. Could you spare me some time to answer some questions? Sure. Given the election tomorrow, which party would you vote for?
Opinion polls are a serious attempt to look at the way in which people intend to vote. Yet opinion polls don't ask everyone's opinion. So why do pollsters expect us to take their findings seriously?
It's difficult to believe, but a representative sample of, let's say, 1,000 or 2,000 people has the same statistical reliability in the Republic of Ireland with 3.5 million adults as it does in Great Britain with 40 million adults, as it does in the United States with 180 million adults. Well, how can this be?
It's rather like eating a cake. You don't need to eat the whole cake to know what it tastes like. You only need a small slice. And that works in opinion polling as well. We don't need to know what the whole population thinks by asking the whole population.
A vote for Liberal Democrats is a wasted vote.
Yes.
If there was an election tomorrow, which party would you vote for?
Labour. It's in much the same way that I know what the Thames is going to taste like by drinking a small amount of it. I don't need to drink the whole of it, I can actually tell. And providing I actually have a representative sample of the whole population, then a smallish number of people will enable me to predict what the whole country is actually thinking.
The key seems to be the type of people that you ask. They need to be representative of the population that's likely to vote. Pollsters say that to be accurate, you have to ask at least 1,000 people how they expect to vote. But where do you find them? Can you simply pick them off the street? Well, not if you want to represent the whole population. Statisticians say the most reliable method is to use what's called random or probability sampling. Suppose you randomly select 1,000 names from an electoral register, so everyone has exactly the same probability of being chosen. You could then call on those named individuals and ask their opinions. That would allow you to learn about the whole population just from the sample. But it's not what opinion pollsters do.
The choice of which sampling method to use is really a trade-off. It's a trade-off between speed, it's a trade-off between cost, and it's a trade-off between the need for accuracy. The basic decision is going to be made between a probability sample and a quota sample. Probability sample with everyone having equal opportunity of selection. The quota sample, the interviewers being given the opportunity to choose respondents between perhaps a certain number of men and a certain number of women, a certain number of younger, middle-aged and older people, a certain number of middle-class people and working-class people and the like, against quota controls derived from census data, usually.
Hello, I'm interviewing on behalf of...
Stopping strangers in the street, the pollsters ask questions that categorise the respondents. And by fulfilling preset quotas, they can take a snapshot of public opinion at any one time.
The kind of sampling that's normally used for opinion polls is what's called quota sampling, where the interviewer is instructed to find so many people of different types, so many men of a certain age group who are working in a certain class group, and so on. And by representing all the different age groups, the different sexes, class groups, and so on, we can build up a small sample which is still fully representative of the whole population.
It's very important with any opinion poll to ensure that the sample we do take is really representative of the population, whatever population we're trying to measure. Typically, when we do surveys of the general public, we ensure that the sample is distributed geographically across the country. And within each sampling point that we choose, we ensure that the sample is representative by the demographic profile of the population that live within that area. For example, by age, sex, social class and working status.
But because the pollsters don't speak to everyone, the sample won't reflect the population exactly.
if, for example, you take a coin and you toss it up in the air, then the proportion of heads and tails that you should end up with would be 50% heads and 50% tails. And it's obvious the more times you toss the coin in the air, the more likely the answer is to approach 50-50. And as it is, so it is with sampling the population as a whole. Of course, there are 43 million voters out there, and if we start by interviewing only 10 of them, then the results will not be representative. But as we increase the sample size, so we should approximate to, start to converge on the results that we would get if we went out and asked all 43 million.
Common sense suggests that as sample size increases, the sampling error decreases. And statistical calculations confirm that with a sample of 1,000 people, the error is roughly plus or minus 3%. This falls to under 2% for samples greater than 3,000. So, did the pollsters get it wrong in 1992 because any results based on a sample are subject to sampling error?
The opinion pollsters have begun an inquest into why they apparently got the results so wrong. The Market Research Society says it's launching an immediate inquiry. On the night before the election, the BBC's poll of polls showed the Conservatives on 38%, Labour on 39%, and the Liberal Democrats on 19%. 4 opinion polls were used to get that result: Gallup, Mori, NOP, and ICM. The large total sample size of 8,141 people suggested a margin of error of 1.5%. That meant the Conservatives could have been as high as 39.5%. Labour could have been as low as 37.5%, with the Liberal Democrats on 17.5%. The actual results were well outside the margin of error. The Conservatives actually got 43% of the vote, 3.5% higher than the poll suggested was possible. Labour ended up with 35%, well below the figure suggested by the margin of error. Only the Liberal Democrats, who ended up with 18%, were within the margin of error.
It's unlikely that the sampling error was the main cause of the problems in 1992. So what about the quotas themselves? How appropriate were they? Comparing pre-election polls with exit polls, carried out as voters left the polling stations, one company, National Opinion Polls, found that 70% of their sample were homeowners. But in their exit poll, this figure was 75%. They found that council tenants were 23% of the original sample, compared to 16% in the exit poll. NOP figures for social class tell a similar story. 42% of the campaign sample stated that the head of household had a white-collar job, but this figure was 54% during the exit poll. With manual blue-collar jobs, the balance is reversed. 58 in campaign polls, but only 46 on election day. Those findings were similar for most of the polling companies. What this meant was that the pre-election quotas contained a bias. They were too strongly slanted towards those more likely to vote Labour. Why was this?
For the most part, the opinion pollsters rely on a survey known as the National Readership Survey, whose primary purpose is, in fact, to get a reasonably accurate measure of the relative readership of newspapers and magazines, and not necessarily to acquire an accurate social profile of the population. And certainly comparing the results of the National Readership Survey in 1991 with the results of the census undertaken in that same year did seem to suggest that there were some discrepancies between the social profile of the population as measured by the National Readership Survey and that of the census, and that in particular it would appear that the National Readership Survey suggested that, broadly speaking, the population was a little more working class than it actually was.
Quota sampling has its problems, but even some academics agree that these may be preferable to the problems of random sampling.
There are two main reasons why polling companies don't use random sampling techniques. The main reason is cost. It's actually very expensive to go and find a specific person when that person isn't in, to go back, to call again, and to keep on calling until you find them. The sheer cost of that, obviously, is enormous. The second problem is a problem of response rate. What's very clear on the basis of random sampling, of going to specific targeted people, is that the response rate of those surveys are actually quite low.
Polling companies need to decide between probability and quota sampling. But what role do the media play in this decision? After all, they commission many polls.
Probability sampling is wonderful if you have the money and the time. But a decent probability sample takes 2 or 3 weeks to conduct. The hard truth is that in politics, especially in the rush of a general election campaign, there's not the time to conduct a good probability sample poll. The truth is, it has to be quota polls in a fast-changing political environment. The challenge to the pollsters is not to move from quota back to probability polls, but to get quota polls right.
And they had 2 polls, one quota sampling and one random sampling that had errors more significant than any errors.
It seems certain that the arguments about random versus quota sampling will continue. But the problems associated with the quotas still only account for some of the error in forecasting the 1992 outcome. The Market Research Society report also blamed late swing as a factor.
Opinions as the ripples on the surface of the public consciousness, shallow and easily changed.
Late swing can be people moving from one party to another, or it can be those people who didn't know or said they didn't know what they were going to vote for immediately before the election, but then ended up voting a particular way, or alternatively people who said, I'm certainly going to vote this way, but then didn't go and vote.
The evidence of late swing itself came from panel surveys, that is, surveys in which people who had been interviewed before polling day were again interviewed thereafter. What those panels indicated, broadly speaking, was that there was a movement of the order of around 1% or perhaps 2% from Labour to the Conservatives, but there wasn't a sufficient movement amongst these people to take up all of the difference between the 1% Labour lead that the polls were indicating and the 7.5% lead that eventually pertained.
Although the ballot is secret and no one knows which way people vote, it seems from the result that people who were undecided before the election were more likely to vote Conservative.
My own view is that Sheffield Rally frightened the troops. The week before polling day, Labour had a triumphal jamboree in Sheffield. 10,000 people stomping their feet and cheering Neil Kinnock. Kinnock went hyper.
Well, all right.
About 10% of the people who said they intended to vote Liberal Democrat in the election the following week didn't support the Liberal Democrats, most of them going home to the Tories. That, I think, was enough to swing the election.
So late swing was also important. But even then, the effects of inaccurate quotas and late swing were still not enough to account for the difference between the pollsters' predictions and the election outcome. To explain this difference, the Market Research Society turned to another theory.
I'll tell you what, it's not just me, but see with this by-election. There's a great many things crawling out from underneath the ground.
Excuse me, sir. Can I just ask how you're going to vote in the by-election?
Communists! Without a doubt, communists! Tell them then, shut them up, you know.
Excuse me, sir. How are you going to vote in the by-election?
Liberal Democrat. And I don't know. He touched us that now.
A German pollster called Elizabeth Noel Newman, who's been polling for 40 or 50 years, developed in the 1970s a theory called the spiral of silence, and it's worked very strongly in Germany. And what Elizabeth Noel Newman found was that when a political party or a point of view was generally deemed to be unpopular, then people who supported that party or upheld that point of view were sometimes reluctant to admit it to pollsters.
If you can imagine the period leading up to the 1992 election, during that period of time, the Conservatives were perceived to be unpopular, in the press particularly, and on the TV. And in those circumstances, the theory of the spiral of silence would suggest that there were a small group of Tory supporters who perceived that the vocal majority was in favour of Labour, and instead of actually moving from being a Conservative supporter to being a Labour supporter, some of these people just became inclined to keep their thoughts and feelings to themselves.
According to this thesis, if people believe that a party is currently unfashionable at the moment, perhaps, for example, because they think it's going to lose, that as a result, people are more reluctant to admit to a stranger that they are likely to vote for that party than would otherwise be the case. People want to be thought to be on the winning side, on the fashionable side, not to be on the unpopular or unfashionable side.
Now, any survey has a level of non-contact, whether it's a very quick, cheap survey or a huge government survey with a massive sample and so on. There are always going to be people who don't reply. The problem in '92 seems to have been that Conservative voters were less likely to take part in opinion polls.
For years and years I would have said Conservative, yes. But now, no, I don't know.
I'd probably tell them it's a secret. Well, I always say Conservative and I always vote Conservative.
Well, I don't think everyone who answers these opinion polls would vote for the way they say they would in the reality of an election.
You're the wrong person.
So people don't always tell the whole truth to opinion pollsters. After all, the real ballot's secret, and they may want to keep their intentions to themselves too. But how do you tackle a problem like this statistically? Where do opinion polls go from here?
One of the conclusions of the Market Research Society Inquiry's report was that probably an industry which is all undertaking the same methodology is not a very healthy industry. Opinion polling, like all social science research, is something which is always capable of being improved, and that therefore a pluralism and a sense of experimentation in methodological work is essential. And certainly I think as a result of the problems that the industry faced in 1992, it is unlikely that all the opinion pollsters are certainly in the immediate ensuing years likely to employ the same methodology.
We will be continuing to examine, to pilot test, to take by-elections, to take, as we have the European elections and local government elections, to test different methodologies. We do running what's called split samples, where we take a matched sample of 2,000 people, split it into two halves, 1,000 and 1,000, and use one kind of question wording with one half the sample and another kind of question wording about the other half the sample, and then make the comparisons. And we're testing different sampling methodologies, different fieldwork methodologies, different question wordings, and different indicator questions, all of which will help to inform us.
We're still going to carry on using broadly the same principles of sampling that we used in 1992. We don't believe that there's a fundamental flaw in the principle of our method, but clearly the way we applied it was open to question. We will be looking at a much wider range of sources for our quotas, and also looking at other variables not to set quotas on, but which can be used to calibrate the survey after it's been done.
People would vote while others would not. I would like you to say how likely you think it is that you would...
In light of the so-called spiral of silence, one company has decided to take its changes further.
In particular, we're addressing the issue of the spiral of silence. And the practical changes that we've made to our polls is firstly to introduce a secret ballot, which we think gives people greater privacy to answer what has become a sensitive question.
Right. Can you put across where you actually voted at the polling station and pop both your forms into that envelope?
We ourselves have not found it to make any great difference, and I think the general evidence on secret balloting is it's not a significant factor in changing the results that you get. It's a lot more difficult to implement in the case of an on-street survey than it is, say, in an exit poll. It's ideally suited to an exit poll, and we have changed from using question technique to using secret ballot for the exit poll, where there we're replicating what they actually do in the election. We give them a piece of paper, they mark their cross on it, and we actually have a little ballot box that they drop it into. And that is, I think, seen by respondents as genuinely secret. Giving them an envelope, which clearly is going then back to the interviewer, is a bit of a halfway house, and that may be why we failed to find any significant variation from using it.
It's in here how I'm going to vote. If I'm going to vote for the Conservatives, I'll vote
If not, then I won't take notice of public opinion.
It's only the floating voters who I don't think will give a true impression anyway, because they won't want anyone to know which way they're vacillating.
I know, but not necessarily will stay.
But it's not only the introduction of secret ballot polling that makes ICM different. They're attempting to end the spiral of silence forever.
The other major thing that we're doing differently is to look very carefully at those people who say they're certain to vote, but who say they don't know what they're going to vote, or they refuse to answer the question, because we count those people as being caught in the spiral of silence. And if we look, we can see that a huge proportion of them currently admit to voting Tory last time, which is consistent with the spiral of silence, and it's consistent with the very negative publicity that the Tory party is getting in the press. And we ascribe some of those people back to the party that they voted for last time on the basis that they would indeed return to the party they previously voted for when it actually comes to a general election. And that rather reduces the gap between the Tory and the Labour Party, because obviously we're adding more Tories back.
We believe that Labour's vote is up 8%. Up 8%.
The spiral of silence may be here to stay. The value of changing polling methodology will only be known with time. So where does that leave opinion polls?
All that the opinion polls can do is to try and re-establish their reputation by getting it right in by-elections, getting it right in local elections, increasingly in the run-up to the next election.
I've absolutely no doubt that unless the House of Commons bans opinion polls at election time, polls will play just as much a part in the life of politics and the media as they've done in the last 20 or 30 years.
Learning zone actually is a supplement to our college work. It enhances my understanding in my coursework and broadens my knowledge power. The learning zone is quite useful to us.
And that's BBC